Good morning, everyone, and warm welcome back to day 2 of the conference. We'll start with, can everyone hear me? Yeah. We'll start with a talk by Dominic Widows on composition with qubits, some building blocks for quantum semantics. Thanks, the stage is yours.
Thank you. So, composition, some building blocks for quantum semantics. This is me, Dominic Widows, and it's work with colleagues Darway and Chase. And, well, here we are. And we work for IonQ. We make quantum computers out of trapped ions. So start with thanks and much appreciation to the conference organizers. I think for a lot of us, this is, our first social outing to a conference in, 2 or 3 years, in fact, for me, since the last time I was, well, not standing here, but standing there, but otherwise very similar. So huge thank you, and thank you for the wonderful setup here and the conference dinner and the wonderful choice of wines last night, and thank you all for making it here this morning, given the wonderful choice of wines last night. So going to talk about, quickly, why we're interested in Quantum AI and NLP, but we are all interested in Quantum AI and NLP, so I probably don't need to convince you. That'll go fairly quickly. Mathematical background, vectors, tensors, projections, similarity. Again, that'll be quick, because you lot know it. Well, of course you do. Language background, there's some interesting stuff, partly just in how long we've been using vectors in language that we sometimes forget today, so I'll go over that very quickly. And then the main meat of the talk is the near-term advances, the composition with qubits, and we have, I've got an additive application, a sequential application. This one's for bag of words topic classification. This one's for bigram modeling, and there's one at the bottom, ambiguity resolution, which should be there. So, why is quantum AI interesting? Well, there's all sorts of reasons people talk about. There's building some sort of real general intelligence is a core goal of computer science anyway, and there's reasons for believing that quantum models, quantum computing, will fill crucial roles in truly intelligent systems. There's all sorts of reasons people have said this. There's, Roger Penrose is perhaps the most famous for taking a very literal approach to quantum cognition being literally quantum processes in the brain. But there's other things that, we know that humans have access to much more information than we ever use. And if I just look around the room, the number of photons hitting my eyes, the number of people I'm seeing, but apparently I'm processing something like 40 bits a second, according to some psychology experiments. And so we're astonishing at taking in lots of information, but only really accessing or using or thinking about a relatively small amount of it. So these could be word meanings and associations. It's astonishing how many meanings and associations words have, and very few of them trigger at once because we don't need them all at once. And this starts to sound a little bit familiar. You've got 2 to the n variables, but you can only measure n bits. Oh, yeah, that's something of an overlap. I mentioned a word may have many potential meanings, and we pick one in context. And by a structural analogy, this is like measurement in quantum mechanics. And when I say a structural analogy, I mean it to sound, a little bit, well, that's just an analogy, yes. It's also an analogy that's been used to describe prices in economics. It's that you don't really know what the price of something is until you strike a deal and money changes hands. I know we have price tags on things nowadays, which kind of makes us forget that. But as soon as we're actually negotiating the price of something that isn't mass-produced, then of course, prices are things that come into existence by transactions, which are a kind of measurement. And decisions in psychology have been described very similarly. It's not that you know what decision you're going to make in advance, and then so someone asks you and you tell them the decision you had already made. That making decisions is an interactive process between us and the environment that we're operating in. And also, we very quickly access information when we need it, even if this is unexpected. Now, this is something that computer systems in general have failed to do. We have a very component, ball and spoke, inputs and outputs approach to software design, computer design, building components. Now, of course, that's not the only way we build software nowadays. In fact, that's to some extent the traditional difference between the stack and the heap. But we still don't have very good computational models for, oh, I didn't realize I needed this information, but I need it now, I'll go and get it. And if any of you have experience trying to get state that you didn't have in a distributed system that wasn't designed to give you that state, it's miserable. And something like any-to-any connectivity could be crucial here. And so that's not just quantum computers or all of them, it's thinking about the topology of quantum computers, and is that something that we really need to think about from the point of view of intelligence if we're going to build intelligence. So, a bunch of interesting overlaps. Okay, so now skedaddle through the background, and when I say mathematical background invitation, what I mean is it's an invitation to, if I go over any of this too quickly, love to talk about it for hours during breaks, etc. So anything in the next few slides that I go over too quickly is really asking, come and talk to me afterwards if you've got time on your hands. Right. So we know that quantum states and wave functions are represented by vectors, Fourier series, all that good stuff. And quantum operators are represented by matrices or tensors that act on state vectors. And matrices are not exactly the same as tensors. They're rather more impoverished. It's something that we should discuss more in AI at the moment because tensors have become all the rage in AI, but we're often not thinking of them as any more than matrices, and in particular, you can't do duals that way. Just quick thought experiment. You're probably used to the idea of a scalar product. You can represent it as a column vector multiplied by a transpose column vector. Try turning any column vector into a transpose using matrix multiplication. Dimensions don't add up. You can't do it. So you actually can't develop a full vector calculation system that does all the things we're used to doing with vectors with just matrices. So that's an interesting motivation for actually looking into what tensors really are and duality and the sort of type arity. And I need to keep moving on because this is not meant to be a math talk. Right. So when we perform a quantum measurement, the probability of each outcome is given by the square of the scalar product. So that's the probability amplitude. And this is cosine similarity in AI and machine learning. We're great at using different names for the same things. And this leads to a whole logic of projection operators, and this quantum logic is non-local, non-distributive, and having already rambled a bit too much about mathematics, again, if anyone wants more on what do you mean by non-local and non-distributive and why is it a logic, love to talk about it. Okay, word vectors since the 1960s. I tend to pop this in because we often don't realize how long we've been using vectors. So the idea of using term document matrices for information retrieval started in the 1960s, or at least is documented at least as far back, I dare say they were talking about it earlier. And Keith van Riesbergen is a wonderful source of information on this, and shout out to Keith as being perhaps one of the grandfathers of this community. And so how do we build an information retrieval system using matrices? We go over a corpus of documents, we count how often each word occurs in each document, we record those scores in table cells like this, and oh, look, as soon as I've got a whole row of numbers, I can multiply them by the scalar, which we often do for term weighting. I can add them together, which we do to create so-called document vectors, and then you can do cosine similarity between this sort of weighted sum of term vectors in queries and documents, and build an information retrieval system. Of course, a ton more goes into building one of today's big modern search engines, all sorts of things like all sorts of things that I'm not going to talk about this morning. Do not digress. All right. But one of the early information retrieval systems, by the late 80s, we were doing all sorts of other things with these matrices. You can project them down to get more information, well, no, to compress the information and bring things together using singular value decomposition or more recent techniques like we mentioned latent Dirichlet analysis yesterday, or a non-negative matrix factorization. Because as in probability, people are sometimes really perturbed by the fact that singular value decomposition creates negative entries. I almost find it perplexing that people are perturbed because, well, first axis is a best fit line. Other things may be above or below the line. Of course you get negative coordinates, but people do seem to find that very strange. But it's not just these vector search models, there's also the connectionist models that have become the enormous juggernaut of neural networks in AI today. They were around in the 1980s. They didn't scale very well, so people lost interest to something. Well, that's unfair. They were not widely used. And of course, the computational scale by 2013, then neural network ways of building semantic vector spaces became very big very quickly. Like, took the community by storm, and now everyone is using word vectors or even like character vectors and collections of character vectors, the so-called contextual embeddings. I do find it somewhat unfortunate that the term embeddings rather than vectors were used for this, because it's led to a whole way of talking about this field that makes people think it started in 2013. That's a problem not just because I'm a bit old and grumpy about it, and we were talking about it long before it was fashionable. I am a little bit old and grumpy about it. But the real reason I'm bothered by this is we've thrown away a lot of things that had to be reinvented later, like, for example, the projection logic, or indeed this strange belief that percolates the NLP community and is often repeated that, oh, you can't use a vector to represent an ambiguous word because it's just a point. That's just fundamentally not true. It's plain wrong. Yes, vectors go directly back to Euclid's axioms in a beautiful way, so a point is that which has no parts. Yes, but we've done so much more with vectors since then. We have, it's almost as if the language community, it sometimes feels like the language community, the NLP community, is caught up with Euclid and not got as far as Fourier, which is strange. So, yeah. Yeah.
Famously combines grammar and meaning.
Yeah, yeah, absolutely. If I was going to talk about this particularly, Paul Smolensky's work on that role filler binding in the late 80s, using that for slot filling syntactic structures, and they're still doing, like Paul's group is still doing fantastic work today. They gave a wonderful talk in the Vector Symbolic Architectures group recently, and that's wonderful stuff.
Because the other ones are not doing that.
That's true. Well, yes, quite right. And the neural net composition, the things that we're using, like for those in sort of BERT kinds of models, are generally not taking syntax very, very seriously. All right, so I popped this in, so I do want to talk about what we're doing now, but Bob reminded me last night that there's a whole background here that some of us take for granted because we've been friends and talking about these things for a long time. But let me quickly mention, my interest in word vectors started in the early 2000s. I was lucky enough to get a postdoc after working in pure mathematics, working on this high-dimensional representations for machine learning and language. And one of the first challenges I faced was this comment Semantic vectors, they can only do similarity and addition. You can't call that semantics. You can't even do negation. That was the first day I met Oliver Lemon, who was one of my colleagues at CSLI at Stanford. And it was a perfectly friendly chat over coffee, and then we started playing guitar together. It was but I thought, what a good point. We can't do negation. You know, challenge accepted. Well, we can do negation. If you want to get a vector for something like A not B, well, then it should have no similarity with B. You've removed the B parts. Okay, well, how do I make sure two vectors have nothing in common, no similarity? Oh, I can do that with orthogonal projection. Well, shall we try it? Well, of course we did. And it worked very well for removing unwanted meanings from search results. You don't just remove the unwanted word, you remove a lot of neighbors of the unwanted word, and it worked for word sense disambiguation experiments as well. And so it took a couple of years to publish. How can something so simple take such a long time to publish? It took a while, the whole, evaluation, results, is it really working? Do people like it? No. Okay, more evaluation, more results, do people like it yet? Yes, okay, then we got it published, good. And it was very fortunate that we did, because I got this wonderful piece of feedback from, I think it was Larry Moss at Indiana, saying, you do know there's prior art for this? And I was, oh no, this is bad. This means someone's done it before. It probably came out at ACL 2002, and it's 2003 now. I've been scooped. No, it's been done before by these people called Birkhoff and von Neumann from 1936. And I was just like, I wasn't quite who are they, because, but mainly knew about von Neumann from von Neumann boundary conditions in my differential equation course. And was, oh, yeah, I know, they did something in quantum mechanics. Is it related? And here we are 20 years later talking about quantum AI and word vectors. And raised just an interesting little thing on, well, by negation, do we mean things that are perpendicular or things that are opposite? And, well, yeah, it could be both. Here's my suit vector, which is a combination of clothing and legal meanings. If I project it, if I want suit, not lawsuit, not the legal meaning, then I project it down onto the clothing the clothing axis. And it's just interesting that that does raise the question, when we say negation or opposite, should things be opposite or should things be orthogonal, we use both pictures in quantum mechanics, that these are orthogonal vectors and we represent them as antipodal points on the Bloch sphere. All right, so why are people interested in this right now? The real reason, well, one of the big reasons, we've been doing these things with quantum models for a long time, but now we have quantum computers for real. And that's what's made the last couple of years this sort of uptick in excitement. It is a great time to be working in this field. It's so exciting. And so this talk's going to be principally about the new things that we're doing on quantum computers. I mentioned IonQ makes quantum computers using trapped ions. And most circuits in this talk were run on an 11-qubit machine, though some of the things in the bag of words classifier I scaled up to 20 qubits for the first time last week. So all happening at the moment. And so the field is moving from theory to practice very quickly. So we've talked yesterday about some of the algorithms that we've had for 30, 35 years. But they've been theoretical algorithms, just in the sense that, we had celestial mechanics for hundreds of years before spaceflight. It's not bad to do theory before practice, but we can do it for real now. And so the field's moving from theory to practice very quickly. I'll say it's a good time to be perfectly opportunistic, that for the next couple of years, we're going to be able to ask, has anyone done this on a real quantum computer yet? And if they haven't, go ahead and do it, because in a couple of years' time, yes, they will be all running on quantum computers. And this is really important for us to do. So yes, everything runs on simulators as well so far. So my development process is not I have a quantum computer sitting on my desk that I play with all day. I still, generally speaking, always try things out in simulation first and make sure everything runs before I start submitting jobs and waiting for results, etc. But the simulation has become just one of the development steps. It's like saying, okay, my code compiles. Well, yeah, but does it run for real yet? And now that it can run for real, let's be doing that. And it's also enabling us to think and talk about what do we really mean by quantum advantage. I think one of the things I find myself not liking is when we talk about quantum advantage, because there are quantum properties that can change complexity classes of certain processes from exponential to polynomial, it encourages us to think quantum advantage means changing something exponential that doesn't actually run yet to something polynomial that still doesn't actually run on a quantum computer yet. So there are so many other things that are advantages of quantum computers, like 2 to the n variables in n qubits. Like that's my quantum advantage right there. My job is to use it. And that's not the only one. And so that's really, if there's any takeaway sort of encouragement, I'll probably dwell on this point again at the end just to emphasize it. One of the biggest contributions we can be making the next couple of years is running things on real hardware. And before anyone says, well, that's easy for you to say, you work at one of these companies that's got one of these computers. Look up IonQ research credits. That is one of the ways that you can start running circuits on real hardware. There's an upcoming deadline on June the 30th for proposals. So if there's something you'd really like to get running on a quantum computer, do chat with me afterwards, do apply. This is something that we can all be contributing to. All right, so the near-term advances in composition with qubits, the actual meat of the talk. What have we done on these quantum computers? Okay. We're doing this right now. And so, first example, bag of words classification. And what do I mean by classification? In this context, classifying texts to topics. Standard NLP challenge. We use it for all sorts of things like sometimes keyword tagging, sometimes customer service, like message routing, intent classification in dialogue systems. There's all sorts of parts in language processing systems where they do some sort of classification. And this is something that has been run on quantum hardware. That's one of the exciting things between the last time we were here and this time. So shout out to the team at Cambridge Quantum Computing, as it was then, Quantinuum now, for really getting the ball rolling here. Not just in doing the experiments, which is great, fantastic, but also releasing the Lambek package and the data set. So there was me looking around for, how can I find, where's there a data set that I can use for classification experiments that's big enough to be interesting, small enough to be real, and already has, ideally, someone else has done the work, and someone else has, you have prior art to follow. So thank you very, very much for that contribution. And so here we extend this work with alternatives. And if you think about NLP from the point of view of linguistics, it's very natural to think about meaning in terms of syntax and semantics. There's a long tradition in linguistic theory in logical semantics of building semantic representations on top of syntactic parse trees, or some syntactic form. And that's one way of doing it. And coming from an information retrieval background, naturally, I did something grubbier. In information retrieval, we don't normally think of syntax and semantics. We normally think of, term weighting and relevance. Those are the sorts of topics we talk about. So naturally, from that point of view, if I'm going to try and build a classifier, it's like, you're not going to just split the words up and then assign numbers to them and add them up and hope something good comes out? Of course I am. That's exactly what I'm going to do. So, partly, that's a good, interesting challenge because it raises some good mathematical questions as well. How do we add classifier weights? 10 minutes left? All right, good. Okay. So, in that case, I'll get through this quickly. 'Cause one of the things we often do, not just in classifiers, but in neural networks of all sorts, is adding weights. So, for example, suppose that bread and butter both have high scores for being related to food, then bread and butter together should have an even higher score. Right. So this task's done using partial rotations and CNOT gates, and this uses the famous in-between states that single qubits can have, unlike classical bits. We perhaps talk about that too, it's too popular to say, oh, quantum computing can represent in-between states. Yeah, so could analog computers between the 50s and 80s, and then we stopped using them because floating point arithmetic was fast enough and accurate enough. But it is one of the benefits of quantum computers. And so if I build a circuit like this, it turns out after a bunch of maths, it produces outputs like that, which, as you can see here around the origin, are going monotonically increasing in both of these angles, but it produces interesting shapes as we go globally. And you can represent single qubit rotations using quaternions. It's really easy to take fractional powers of quaternions using De Moivre's theorem, and then you can build up different algebras using different quaternion generators and make all these pretty patterns. And I could stare at these for days. And but I have not just gone back to being a quaterniist and studying this the whole time, much as I would be tempted to. So how do we build this into a classifier? Well, during training, okay, we picked the 9 most salient words in the corpus, so that a lot, not a lot, a little bit of manual tweaking there. Again, sort of simulation, development process, get it working, then run it. And so during training, we go through the corpus. So, for example, if you had just 2 words, you do those 2 rotations. Then during classification, when you see a new word, a new document, you connect it to a sum classifier bit for each of the topics, and then just see which of these sums wins in the sense of when you measure them, like which gets the most ones over a number of shots. And that worked very well. And first off, had to run it in 2 different runs, like 9 qubits per topic, so that was 2 jobs, combine them afterwards. But now I can run it all in a single run, and it produces the right results. Yay! All right, moving on. Bigram sequences and distributions. So the composition in the last one was, well, the only composition that's going on really is adding things up. Going back to Oliver's original complaint, well, that's not really semantics, you're just adding stuff up. Well, it's a part of semantics that we need to be able to do, but we shouldn't stop there. So, bigram sequences and distributions. Okay, started with 1, moved up to 2. Very bottom-up approach going on here. But even bigrams in language are interesting in themselves, not just for building language models for like Markov model parsers and things like that, but, for example, in dialogue systems, arrange accommodation, book room, reserve hotel, make reservation. They're all different ways of saying the same thing. And one of the things we don't even note necessarily is book and make, for example. They're not synonyms, but they are in book a room or make a reservation. So how did we model this? There's a whole literature on modeling joint distributions using quantum probability. You collect example pairs, so red apple, green apple, yellow banana, encode as a state vector, and then you take the outer product of it with itself, take partial traces using the density operator, and the interesting thing you come out with, which is different from classical marginalizing a classical joint probability, is, oh, these off-diagonal elements. Oh, red and green have some sort of relationship between them. That's very nicely described in quantum probability. Here's going through the steps in more detail. More to say, it really is that simple rather than it really is that complicated. That is all you have to do in this experiment. And so then we approximated this small distribution with a quantum generative model, and Interesting thing about that was noise in the image blurring was mentioned yesterday. We actually got better results fitting this distribution by allowing there to be some noise. And then we actually want to use this for generation as well. And then we asked this sort of noisy fit to start saying, OK, tell me other plausible phrases. And, you know, it had been given black shoes to begin with, and it came out with things like, you know, brown shoes, good. Also came up, you know, occasionally we got some, you know, strange things like, you know, purple apple. Yeah, you don't get that for real. But there's plenty of opportunity to scale this up and start doing like more thorough evaluations on that generative process. Finish with ambiguity resolution. Ambiguity, hallmark of language, it's the rule, not the exception. It's very nice to leave ambiguity in the corner and say, oh, well, let's just assume everything's disambiguated before we start doing our clever syntax and semantics, because ambiguity is, you know, it's a side issue. It's not. Ambiguity is everywhere. More than half of the most common words in it, most common verbs in English are nouns as well. But we don't even think of them as, you know, we syntactically disambiguate them and don't think about that. All right. We've been using vectors, have a long history with ambiguity. How long do I have left? Like 2 minutes? All right, great, fine. And particular shout out to Henrik, who was the founder of the project, well, in fact, started the work at Stanford on vectors that I was lucky enough to get to continue, and we were looking at, so it was Henrik's work on word sense discrimination that led directly to us trying to find that empirically in the orthogonal negation work. And composition helps to resolve and sometimes demonstrate ambiguity. So like set, point, set, line, like these mathematical words, the words we use in mathematics are also some of the most ambiguous words in English. So set theory or set yogurt, set square, a set winner. This is like tennis, carpentry, you know, they're all different. And we don't think about that often. We just know what it means. Matrices can implement something that does this. So again, this is well known by now. Marco Baroni and Zamparelli did a lovely paper in, I think, about ACL 2012. Nouns are vectors, adjectives are matrices, or the title might be the other way around. But if you look up adjectives, nouns, matrices, that's one of the papers you'll find. And the matrix multiplication does a good job of picking the components that matter to it, and so that can be used for disambiguation. Here's a toy domain example. So we just have 4 different topics: places, events, tech, and skill. Borneo is a place, C++ is a tech, a trip is an event, juggling is a skill. Java, I picked as my ambiguous word here, could be both a place and tech. And so then let's look at some of the verbs that could be represented as matrices. So visit, for example, takes a place and turns it into an event. If I visit Borneo, then there's an event happening. Right? Similarly, if I learn C++, then I acquire a skill. So somehow learn is taking a technology and turning it into a skill. So that's what these 2 toy matrices do. That's also what these little circuits do. If I have Java that has activated both the place and the tech axis, but visit takes a place and says you've got an event, then, oh, what does this circuit do with the tech part of Java? Just completely ignores it. So in the process of composing visit and Java, we've performed the disambiguation. This was, you won't be at all surprised, this was the trivially easiest thing to code up and run on the quantum computer. Shout out to, well, I'll show you actually running it on a quantum computer, or not, well, I can't do that live here, but it would take a little bit too long to queue and come back. But I can do it with this like Qiskit simulation. And so what have I done? Declared a quantum circuit. There's the bit, 0th bit, 2nd bit, connect 0 and 5. And then I print out the operator. Holy heck, what is this monstrosity? I have no idea what this is telling me. Okay, let me try printing out the state vector instead. Let's run that too. Oh my goodness, it just got worse. I'm saying this, but this is what it feels like using coordinates and NumPy arrays the whole time. I'm mentioning that as part of the quantum development process. I haven't been using diagrams yet, but this is why I should. How much time do you spend every day worrying about byte ordering? I'm guessing 0 in your case, right? Yeah. Okay. So things that will make it real over the next couple of years, let's get results, data sets, precision recall, clear comparisons with alternatives. We want runtime characteristics, how many machines, or which machines, how many shots, how did it actually run? Because people want to know this. And to put it a different way, I often find theoretical papers want to hide a lot of the dirty laundry. Those zeros and ones I just show you, you're not going to print those in a paper. They're horrible. Practice wants to see the laundry go in dirty and come out clean. So let's be doing that. So where next? Scale, scale, scale. Let's make it bigger. It's language challenges. Look for problems that are rewarding at intermediate scales. I think there are several. Happy to talk about those. And keep trying new circuit models. We're going to be doing this anyway. But it's important because it's a place where applications and hardware can come together and discuss what do we mean when we say things are working or we're getting errors. What do we mean by errors in the sense that so much of computing is figuring out what sources of error, or so much of machine learning is figuring out what sources of error really percolate up to errors that affect users. And so, yeah, don't wait. Get involved, use what we have, ask where we can help. Big opportunities, big challenges coming up. Thank you again so much.
Thank you very much, Dominic. Are there any questions? Gemma?
Thank you so much for your talk. So I understand that the problem we're trying to solve is really difficult, but I wonder, how many of your claims or your ways of solving problems can actually be extended, or can you ever make any claim about the extent of your result, like the extent of your claims? Namely, you solve some examples, but can you ever get an estimate or an idea of how they extend? What is their scope beyond your examples? For example, I know Java means two things which are very different, but it's an accident, right? Someone decided to call that whatever. I don't know the story. I don't mind.
Yeah.
So the way you solve the problem with Java does not generalize to many others. So yeah, so can you ever go beyond? Can you ever extend your claims to the things you're not seeing? Like get a grasp of this counterfactual. They're not counterfactual, but they're all these sentences which you're not covering with your examples, and by extension to other languages. Can you ever say whether your ways of solving problems for this specific example of English, how they extend to other languages?
Would you mind repeating that question roughly for the audience online?
Right. Such an amazing, wonderful question that there's so many things we could talk about, so I'll repeat the bits I'm going to manage to answer right now. Questions, can we extend that way of treating ambiguity to more interesting, more systematic forms of ambiguity? And not directly like that. Because ambiguity is fascinating, and so much of it is not accidental. Like, we are in a church, it's a building and an organization. That's not an accident. That's a very systematic way of talking about, if we say, the bank is open right now, it means probably the door is unlocked and you can physically walk in, and you can go in there and do business. For example, if I walk into a bank, open the door, and they say, sorry, we're closed. That means the business is closed, not the building, because I just walked into the building, but I don't even notice that. Now, I can't solve those problems by saying, it's one or the other, always pick one. And that gets into the whole theories of polysemy, can we do those systematic sense extensions in vector semantics? And yes, fascinating, and there's a ton to talk about there. Not very easily, and it's not very easy to do. So it's a really fascinating question that we're at the beginning of in many ways. The other question, does this scale to languages, or does it move to languages other than English? Yes, and there's lots of fascinating things you need to do. There's lots of fascinating things you could do to make it better in English. But for example, word vectors don't scale to Spanish as well because of all the clitic pronouns on the end, like help me in English, 2 words. In Spanish, ayúdame, and that becomes ayudalas, ayudales, and they're all different words. You can get very sparse space. So, well, you can do nice things with that. Well, okay, why don't I just use some basic stemming? Or in that case, I could just do a basic lookup if I don't know a word. Do I have anything in my lexicon that has a prefix? Our German decompounding, if you get a cache miss, if the word isn't in the dictionary, then 4 characters in the word split and see if each part hits, and you can get an extra 2 or 3% in precision just with that little parlor trick for German. So yes, it works for other languages, but other languages often raise fascinating challenges that are there in English, but less apparent.
I think in the light of time, we thank Dominic again. Thank you very much.
Thank you.
Right. It's a pleasure to have Martha Lewis speaking about modeling ambiguity in metaphor with density matrices. Thank you very much, Martha.
Okay, thank you very much. Thank you very much to the organisers for inviting me. It's definitely one of my first in-person events that I've been to, so it's lovely to see people in person again and actually meet some people who I've only seen on Zoom. So yes, I'm going to talk about modelling ambiguity and metaphor with density matrices. So Dominic's given quite a good lead in because he's said, oh, you don't need anything complicated to do it. You can just do it with vectors. I hadn't prepared for that. So we'll see what I come up with.
Can we do the simple bits? So
okay.
Follows from Gemma's question, you might be a better answer.
Sure. Okay, so something that I'm interested in general is how concepts compose, and we can think of concepts as being mediated by the language that they're expressed in. So if you just read these, then as you read these sentences, you sort of do something where you're creating meanings on the fly. You know, you might not have read this sentence about black mamba before. We kind of create meanings here. We're using sort of metaphor here for England's players need to lift themselves, so they're lifting their spirits, they're not actually lifting themselves, and so on. And so what I'm going to talk about is a way of modeling meaning that we can start to use these sort of metaphorical constructions there. Okay, so here's an outline of the talk. I'm going to give a background into categorical, compositional, distributional semantics. Lots of you are probably already very familiar with this, so I'm just going to skate over it quite quickly. And then I'm going to talk about some work we did about 18 months ago now, looking at how to build density matrices to express lexical ambiguity. And then I'm going to talk about how we build these density matrices from large-scale corpora using kind of neural models. So it's going to be an extension of word-to-vec to density matrices. And then I'll just talk about density matrices for metaphor, so basically applying what we already have to a kind of small metaphorical data set, and some further work. And specifically in further work, I'm going to talk about some work that Saskia Brun has done, who is here, and she's kind of taken some of this and applied it on a quantum simulator. So all of this work is done with students Francois Meyer and James Owers. And yeah, so with no further ado, I'll get on with it. So categorical, compositional, distributional semantics. So how should we represent meaning? On the one hand, we could do something that is very suited to composition. We could have some kind of way of representing words and how they compose as some kind of logical or grammatical kind of constructions, and that will tell us how we can go from these individual words up to some meaning of a sentence. And that's been successful. But on the other hand, we can also look at representing words in a more kind of vector-based or region-based way. And that's nice because, for example, we have that, let's say if we have a vector space with dimensions cuddly, smelly, and scaly, then we can see that cat and dog are kind of close to each other, and iguana is further away. And so this closeness in the vector space is supposed to represent closeness of meaning. And so how do we link those two, both of those two useful things? So we have, on the one hand, we've got this sentence, smelly baby cuddles dad. On the side here, we've got some kind of representation of the words in some kind of continuous spaces, and we want to combine those two into one thing. And this is what Bob and Manoush and Steve Clark came up with in 2010, or maybe a little bit before. And essentially, the idea is that this grammatical composition on the left-hand side here kind of goes in, is expressed as these cups on the bottom of the diagram here, and then whatever you decide to represent as your meaning, you set up your meaning representations in such a way that you can then plug the meaning representations onto the top, and this will tell us how to compose these meanings together. And so in in the original work here from 2010, we had that, you know, these triangles with a single string coming out of them are basically vectors. The triangles with more than one string coming out of them we can think of as multilinear maps that you can then plug together. And then these, the cups here, we are basically tensor contraction. So if you're happy with kind of thinking about tensor contraction and so on, that's how you can, if you're not happy about tensor contraction, you can think of it as just kind of an extension of matrix multiplication. And indeed, as Dominic said, there was a paper on nouns are vectors, adjectives are matrices. So here we've got this baby, which is a noun, and smelly is an adjective, and then plugging baby into smelly is just matrix multiplication and gives back a smelly baby. Okay, so So this is nice, and as Dominic did just say, you can do a fair bit of, you can express a fair bit of ambiguity in these ways, and this was actually shown by people like Manouche and Dimitri, who have developed a kind of set of sentences where I'll talk about it in more detail, but essentially the idea is that you want to build sentence representations for each sentence, and then disambiguate the sentences based on which of the two kind of paraphrases of one sentence is closer to the original. So you might have something like shoulders slump and then you could paraphrase that either as shoulders decline or shoulders slump. And shoulders slump is closer to shoulders slouch than shoulders decline. So you can do ambiguity in this way. However, within the sort of vector space model, there is also this natural, this very natural passage to using density matrices for ambiguity. So with density matrices, you're mixing together different states. You don't know exactly which state you're in, and we think of those states as being word meanings, essentially. So vectors for word meanings. So what's the problem with ambiguity? Well, it's been described as by some people as an AI complete problem, meaning that if you can solve this difficult problem, then you're sort of well on the way to solving the whole of AI. You can sort of take that with a pinch of salt, but there we go. And so one of the problems is to disambiguate a particular word given the context. So in this problem here, you might have these two sentences. So there's a lot of trash on the bed of the river, or I keep a glass of water next to my bed when I sleep. And the task there is to say, does bed have the same meaning in each case or a different meaning? And there's a big data set here developed in 2019 that you can use to look at that. And there's also ambiguity in word types, of course. So you can have, I walked up the drive is a noun. It is actually something that you drive up, but I love to drive is a verb. So there's ambiguity in word types as well. And another problem here is that obviously we're not always pointed out which word we have to disambiguate. You know, if I'm talking in a sentence and I can be using words which may have many different meanings, and these are, and what you need to do is you need to kind of disambiguate the words on the fly. And humans are very good at doing this, of course. So in this sentence here, they were troubled by insects while playing cricket. You know, each of these words here have masses of meanings. This one, I mean, you probably can't read it, but this one goes down to 13 meanings. This one goes to 35 meanings. So if you were just going to do it combinatorially, you're going to have a kind of masses of versions of this sentence that you need to then choose which is the correct sentence. And Dimitri and Manouche showed that if you do actually disambiguate word meanings before composing them together, then you get better results. So we can see that if you take a disambiguation step, you get better results. However, we don't necessarily want to do that. Okay? So the solution that we come up with here is using density matrices. So the nice idea here is that we're going to use density matrices. We're going to encode different word meanings by mixing together the word meanings in a density matrix. And then the idea is that as you compose the matrices together, the ambiguity resolves in the composition. And this is what we do. This is kind of what you what we do in real life, and this is what we hope to model by doing this. Okay, so as I said, you can just take these diagrams, you set up your meaning representation in such a way that you can just plug them into the top of the kind of grammar diagram down here. And so when we use density matrices, we can think of these with single legs just as density matrices. We could think of these ones with more than one leg as kind of completely positive maps that take density matrices to other density matrices. And then these cups are now the partial trace. And this was worked out for in a linguistic context by Robin, Pierre Deleu, Dimitri, Bob, and Manouche. And so I'm going to talk about basically, so they kind of set up this whole program on the linguistic side, so I'm going to talk a little bit about what they've done first. So what do we do? So how can we represent a word as a density matrix? Well, given any word vector, we can always lift it to a projection matrix. So if we've got a word vector for cat, we can form the projection matrix that is just cat. You take this sort of outer product with itself. And if, I mean, I'm guessing most people here are okay with these angle brackets, but if you're not, you can think of cat. So this kind of angle bracket is just like a column vector, basically, and this is like a row vector, okay? And we're just multiplying these together. So going back to this example of the riverbed and the bed that you sleep in, then we can take we can find a sense vector for riverbed and create the projection operator there. We can find a sense vector for the bed that you sleep in, create a projection operator there, and then we just mix these together. So we multiply by some probability, like the probability that you actually see it as a river versus see it as a sleeping bed, and add them together. Okay, so that's fine. We can do that, but then we need to actually find these different senses. And what Robin and co do in their paper is they cluster the vectors of the context words that you see. So you take a big corpus of text. You go through looking for the word bed, and every time you see the word bed, you write down what words you see around it, and then you get the vectors for all the so the words you see around it we call context words. You get the vectors for all of those context words, and then you cluster those vectors. So you can use some kind of clustering algorithm, and you take the centroids of those clusters. And you say that those are the vectors for the individual senses of the word. I think that so you can do it in such a way that you don't have to predict in advance how many clusters you're expecting and so on. So that gives us the actual that gives us the density matrices for each word. But so far we've only said how to build density matrices that are all in the same space. So the noun matrices, the verb matrices, the adjective matrices are all going to be in the same space. And so what we need to do is we need to have a way of lifting the matrices for verbs and adjectives up to a sort of bigger space that allows us to sort of treat them as maps, as the maps that we need. And so these have been developed in a few different papers, Bob and Konstantinos and myself, and also me with Gemma and some other people. So one is to use this phaser. So each... so we have phaser, which is, okay, so each of the N and the V are density matrices. You take the square root of the verb matrix and multiply it on either side of the noun matrix, and that gives you back another density matrix. What fuzz does, so I don't know about guitar pedals. I actually called these B mult and K mult, which is...
I think it's more elegant.
Okay, okay. So...
You came up with another pedal, yeah?
Oh yeah, we came up with another one, yeah. So, so which I will talk about in a sec. So, okay, so fuzz is basically you take the spectral decomposition of the verb, and you take the projectors and multiply on either side and then of the noun, and then sum over, take the weighted sum there. So mult is just a pointwise multiplication, but that still is the right kind of map that we need. And then Gemma and I, with some other people, kind of put together this sort of program of thinking about a whole range of operators where basically, I mean, essentially you just have a sort of a CP map that you use to lift whatever your like your verb matrix up to the right size. And then you can sort of work out various options for this compra using just like spiders and so on if you want to. But I'm not going to talk about all of that here, I'm afraid. Okay, so so these are like some options for how to build phrases and sentences out of words. And what did Robin and Dimitri and co do in their paper? Well, they just used mult, and this is just one example. So basically, they learnt density matrices for organ, vessel, queen, nail, and then they also used two different adjectives. So, for example, music organ, body organ, blood vessel, navel vessel. And what this table is showing is that if you have the noun, so the noun is ambiguous, it could be a music, it could be a blood vessel or a navel vessel, and so on. And then when you compose that with the adjective, the von Neumann entropy of the density matrix reduces. So these numbers are the entropy of the matrix, the kind of measure of mixedness of the matrix. And in composition, those values decrease. So there's a kind of demonstration that this works. Okay, so interim summary. We have DiscoCat. We can use it with density matrices, and this gives us a sort of extended way of modeling lexical ambiguity. The hope is that ambiguity resolves in composition, and we've seen that it does. A number of composition operators have been proposed, but then we still have this question, how can we build density matrices at larger scale? So that's where we're going to go now. So our starting point for this is the word-to-vec algorithm. So this was developed by Thomas Mikaloff and various other people. This is the credit for the image. So I'll just talk very briefly about the image. So the idea is we've got x1 down to xv here. V is the size of the vocabulary, and this just tells you which word you're going to try and model here. This gives you there's a hidden layer in the middle, which goes down to the dimension of the vector you want. So the hidden layer, let's say you want 300 dimensional vectors. This hidden layer is going to be 300 dimensions. We've got another matrix of parameters here. And then the idea is that when you put in a word, what you want to do is to come out with a probability distribution over which other words in your vocabulary you're likely to see that word along. And this is what you're training the individual parameters of the matrices to do. and this is the quantity that we're trying to maximize. And what is it? Well, we've got our target word. We take the inner product of our target word with our context word that we do see it alongside, and then we're going to have a certain number of negative samples. And so here we've got the negative of the inner product of our target word with our context word. So we want to make these inner products, where we've got the target word and the context word that we want to see together, we want to make these bigger. So we're going to make these bigger, and we want to make these quantities, these negative quantities, smaller, okay? And then there's some other bits in there you don't have to worry about too much, but essentially we want to make these inner products bigger and these inner products smaller, yeah. So, and then when you've done this training, basically what you end up with is that the vector of the target words are in this matrix here, and then you have another set of vectors for the words considered as context words, which are in this matrix here. And you just take this, and it's going to be, V number of words, your vocabulary size number of words, each having a vector of length 300, or whatever you're choosing. Okay, so that gives you a sort of overview of word2vec. So how can we use word2vec to learn density matrices? Okay, so one naive idea would be, so we're just going to initialize these vectors. Oh yeah, sorry, so we're going to initialize these vectors with density matrices. And then we're going to try again to maximize this quantity, where now we've kind of put in density matrices here instead of words. So what I should have said earlier is that when we maximize this quantity, what we're going to end up, we use gradient ascent, and the gradient is going to have, so this, like the positive part of the gradient, is going to have a small multiple of, let's say, so if we're trying to maximize if we're trying to tune the parameters of the target words, we're going to get a small multiple of the context word that we're going to be adding in to the target word to get it closer to the target word. So if we initialize it with density matrices, this would work because we're always adding in some multiple of another density matrix, which is fine. But here, instead of adding in, 10 minutes, here, instead of adding in, we are subtracting. So we can't really use this directly to build a density matrix. So what we did instead was we said, well, we're going to train some parameters of matrices B, multiply them together to form the density matrix, and train the parameters by optimizing this quantity here. So that was one option. The next option was actually just that we just learn multiple vectors in each of these, and then we mix them together. So the multiple vectors hopefully represent the senses. Another option we had was to use BERT. So we ran BERT over a corpus. We extract like a contextual embedding for each word, reduce the dimensionality of those embeddings a bit, because they'd be quite big if you just used them. And then we mix together those word senses to create density matrices. And what we get in the, and so here's the sort of experiments. So as I said, you could have like something like value slump, value decline is a high similarity example. Value slump, value slouch is a low similarity example. So if I have value slump, I want my representation of value decline to be closer to value slump than value slouch is. And we get quite nice results from this. So basically, the one that works best was the multi-sense word to DM. We find that on, I think, two of the data sets we outperform. For example, standard BERT used as a sentence encoder. For other ones, we don't quite outperform it, but we get. But there's no significant difference between the results. So we get good results there. And we also see, for example, that the mixedness of the representations correlate with the number of senses of a word. And again, we did a similar experiment to Manouche and Dimitri and Robin. And we saw that as you compose words together, then ambiguity resolves as well. Okay, so in an interim summary, so we've got these methods for building density matrices from corpora. The multi-sense DM was basically the multi-sense word to DM was the most successful. Okay, so now how can we start applying this to metaphor? So far we've just done conventional metaphor. So conventional metaphor is when you have a metaphorical word that has been accepted into the language as just another meaning of the word. So we built a paraphrase data set, so it's quite small. We've just got 200 metaphorical sentences. So you might have, he showered her with presents. And then you've got apt paraphrases, so he provided her with presents. It's not a fantastic paraphrase, but it does kind of mean the same thing. Versus he sprinkled her with presents doesn't actually mean the same thing at all. So we tested this with state-of-the-art sentence encoders and also our density matrix models, but all of these were pretty rubbish, basically. So here's the results for sentence. So we've got sentence BERT, infocent 2, and these figures are Spearman's row. Basically, dark red means really bad. Dark blue means slightly good, but not very, and these pale ones mean basically just completely random. So here the correlations were random. Here we don't get a huge amount going on. These are just with plain word-to-vec and glove vectors. What we do see, which is expected, is that if you just use the vector of the verb, then you don't get a good result. And that's to be expected because the vector of the verb is going to be the most common meaning in the corpus, and that's probably not the sort of metaphorical meaning that we want. Okay, so here's a bit of a complicated diagram. I'll just pull out a few bits. So as you can see here, so this is where, so down the side here, we've got various different models that we used. The density matrix models. Here we use the kind of composition operation, which there's no composition, we just use the verb, no disambiguation, we get bad results. Here, these two sets of columns are where we use the verb as an operator onto the noun, and again we get worse results. On these columns, we're using the noun as a modifier onto the verb matrix, and we get slightly better results. So it's kind of sort of saying that the noun is a bit more important here. And then finally, just to point out that actually the BERT to DM density matrix model kind of worked better here, even though it didn't with kind of standard ambiguity. Yeah. Say again. I can't hear, I'm sorry.
Every word is a density matrix.
Yeah, every word is a density matrix. Yeah. Yeah. Normalized, yeah. Yeah. Okay, so you've had time to read the interim summary. So further work, Saskia has done some work doing this on quantum simulators. So she took just the plain word-to-DM model, not the multi-sense model. It's a sort of variational algorithm, I think. You're training the parameters of this unitary here, tracing out over this subsystem, and then optimizing the output based on this, objective function. And I won't go through the experiment because I sense we're running out of time, but essentially she's done an experiment which kind of has nice results. So it's basically a word embedding experiment with density matrices in simulation. Okay, so there's tons of further work to do here. If anyone's interested, do come and do ask me questions or come and talk to me in the breaks. And just to say thank you all for listening, and if you'd like to get in touch, here's my email address. Thank you.
Thank you very much, Martha. There will be questions, I'm sure. Pass on the mic. Manish, did you have another question?
This is about Saskia's work. How did she encode density matrices on quantum computing? How belongs to the larger system or something?
Yeah. Yeah. So I mean, so as part of this. Oh yeah. Okay. So the question was, in Saskia's work, how did she encode the density matrices on the computer? And if I understand correctly, just shout if I'm wrong. So you have this large system, and you trace out part of it, and then you look at these values here. You kind of extract these values. Is that right?
Did you move away from this initial modelization, or are you heading towards a model that would encompass both Hypercube and Ambiguity?
Yeah. Okay, so the question was that density matrices can also be used to model hyponymy and entailment, and is the aim to move towards some representation that can do both, I think. So Bob and Konstantinos, I think, have no, maybe not Konstantinos. Bob and... No, it was... Daniela. Bob and Daniela have done some work on a representation that can encompass both. But there you need to kind of have density matrices of density matrices, so the parameter space gets very big. So what I'm more interested in actually would be to look at developing these neural methods for building density matrices for hyponymy and entailment. So some kind of modification of the word to Vec or similar to do that.
They often go together because hyponymy is often a way of disambiguating.
Yeah, so something we have done is kind of just to take the density matrices that we learnt here and plug them into some ambiguity, some simple entailment data sets, but they don't work very well, unfortunately. Yeah, which is a shame. Okay, so I guess everyone's waiting for the coffee break.
There's
Oh,
one more
oh.
question from the news.
Oh, okay. Yeah.
Sorry, very good question. I actually have 2 questions, but I'll ask both of them. I'm just wondering, what was your task when the sentences and metaphor?
The task, so the question was, what was the task for the sentences and the metaphor? And it's the same, it's a disambiguation task. It's the same task. It's just got a different data set. Yeah, so you're saying, so we're generating paraphrases of these sentences, which is kind of the same, right, as like value slump. So if you have value slump, you could have one paraphrase as value decline, which is an apt paraphrase, or you could have an inapt paraphrase, where you take a synonym of slouch that is in the wrong sense. And that's basic. So the metaphor, the apt paraphrase data set we took from another paper, and then we just generated these inapt paraphrases computationally from like WordNet, and got them rated. Then we asked people to rate them for aptness, basically. Yeah. Okay.
Can I make a small comment?
Mm-hmm.
Because Mark at some point says, okay, this paper was 2010 or a bit earlier. So here's what happened. This guy organized a conference in Stanford in 2007. Then he forced Steve and I to organize the same conference in Oxford. And Steve and I said, okay, we need a paper, otherwise we're going to city. So that was this cat paper.
There we go.
It's the first time in 10 years I think that the three of us are in the same room.
Nice. Cool. Yeah.
That wonderful story, I think it's time to thank Mark.
Cool. Thank you. There we go.
Thank you very much.
Cheers.
So we are Veljkovic from DeepMind and University of Cambridge, and he's going to give us a talk about AI and mathematics. So thank you, Pedro.
Thank you very much for the fine introduction, and that's perfect pronunciation, by the way. So, hi everyone. It is a great pleasure to be speaking here. My name is Petar Veljkovic, and I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And today I'll be telling you about some of our recent work, which showed how even with simple interventions from artificial intelligence, you can make potentially significant impacts on pure mathematics. And it's joint work with all of the fantastic people written on this slide, both from DeepMind as well as our mathematical collaborators from the universities of Oxford and Sydney. So maybe just a little disclaimer before this talk begins. Like, I've really enjoyed the talks yesterday and today so far, and I'd like to just make a note at the beginning that I'm a bit of an imposter in this room. Like, I've done an undergrad course in quantum computing, and I've worked with QML researchers in the past, but that's as far as my QNLP skills go. I've agreed with the organizers that today I'll talk to you about some of our recent work on pure mathematics. But beyond that, I'd just like to preface this talk by mentioning that I am involved in some related pieces of research that might be quite interesting to some of you in the audience, and I'm very happy to chat about them after the talk if you're interested. So I'll just briefly survey them for the first 2 minutes of this talk. The first one you might find interesting is my work on geometric deep learning, geometricdeeplearning.com, which is actually a book I'm co-writing with Michael Bronstein, Joan Bruna, and Taco Cohen. We already have a 150-page proto book out on the archive, and we just recently signed a contract with MIT Press for a proper book release next year. And in this book, what we try to do is we use geometric principles of invariance and equivariance to basically explain all of deep learning as it is today. And it turns out that this blueprint is fairly powerful, because if you have the right choice of domain, the right choice of symmetry group over that domain, and some kind of interesting mathematical manipulations in the middle, you can rederive basically all of the popular or usual suspects like convnets, graphnets, deep sets, transformers, LSTMs, and so on, including some very useful models that live in the middle on more exotic domains like spherical CNNs, mesh CNNs, and equivariant GNNs. So it's quite powerful, and I think why it might be interesting to the audience here is that recently I think 4 influential quantum machine learning groups have more or less in parallel tried to make a quantum extension to our geometric deep learning blueprint. So there was this work from folks at Los Alamos and X. There was this work, exploiting symmetry in variational quantum machine learning. There's also this work on equivariant quantum circuits for learning on weighted graphs, and this work, which came partly from Oxford, partly from Cambridge Quantum at the time, on equivariant quantum graph circuits. So I think there's been quite a lot of concurrent interest in extending these ideas to the quantum domain, and you might find that quite of interest. The second one, which I'm currently very actively working on, I'm trying to get better at learning category theory so that I can use it to unify graph neural network architectures, which is my main area of expertise, and classical algorithmic computation, which is what initially brought me to computer science. And so far, we believe that through the use of polynomial functors, we've been able to get quite far in this pursuit. And we actually have already a preprint on the archive. Graph neural networks are dynamic programmers, which elaborate on this connection in a lot more detail. Unfortunately, I cannot dwell on these for now, but I'd be very happy to talk about either of them as we chat after this talk. Now, on to the main event. The question I want you to keep in the back of your mind during this talk is, can we discover new structure in pure mathematics with the help of machine learning? When we set out to try to answer this question, we actually reached out to several mathematicians we know and trust, and a lot of the response we got initially was super skeptical, even bordering negative. So, like, there's no way machine learning will ever be able to help me in the pursuit of mathematics that I'm involved in. But we actually had quite a strong belief that we would be able to do that, and that's because if you really think about how mathematics is conducted nowadays, it's not just blind application of rules. In fact, very often to make a new mathematical result, one needs a kind of creative leap. There's a bit of creative imagination in there. And maybe the best example of this is Srinivasa Ramanujan, who, without any formal mathematical training, was able to come up with these fantastic conjectures and theorems that basically felt like they materialized out of thin air. So clearly, there's a bit of creativity involved in this kind of whole mathematical process. And maybe one of my personal favorites in making these kinds of leaps from observations, which relates quite a lot to what we've been able to do, is the work of Johannes Kepler. If you're not familiar with his work, he discovered the laws of planetary motion, so how all the planets in the solar system, the laws governing their motion. And the way he arrived at this conclusion was basically by looking at years and years of astronomical data, like just observations of different planets and their positions. And based on that, he was able to spot a regularity in how these planets are moving. And he's famously quoted by saying he first believed he was dreaming when he came up with this regularity. So clearly, mathematics is not just blindly following rules. There's a lot of creativity, there's a lot of imagination, there's a lot of dreaming, a lot of like abstract feelings that can be steered in one way or another as we make our way to new mathematical discoveries. So this is exactly what we wanted to stimulate in our work. Like, we don't want to make an artificial intelligence system that will do all of the mathematicians' work for them. We want an artificial intelligence system that will carefully help the mathematician in critical moments of their work, that they can arrive at conclusions more easily and uncover the structure that's hidden inside complex mathematical objects. So we really want it to be a conversation rather than a replacement. And how we set out to do this, we proposed one possible blueprint in which we can leverage the capabilities of modern supervised machine learning to help certain aspects of mathematical discovery. So let's say if you're a mathematician, you might start by looking at certain objects Z, and you might hypothesize that there are two different quantities you can get from that object, X and Y, and you hypothesize they are related somehow, but there's no proof of this fact. You just believe that it might be the case, or you just might want to investigate the possibility of that being the case. So you assume there might be a function f that maps x to y. What you can do then, using computational tools or otherwise, you could generate a data set of paired x's and y's over some distribution of underlying object z. This distribution is quite important. We'll touch upon it soon in this talk. And once you have this data set, you can train a supervised machine learning model to try to predict y from x. Fairly straightforward machine learning task usually. And sometimes just the act of training a model which gets a high accuracy, and we've seen this directly happen, can really motivate the mathematician, like encourage them that there really is a connection and therefore inspire them to keep pursuing it if there's a model that gets a high accuracy on this data set. But sometimes, obviously, that's not enough. And neural networks, as we know, are typically black box models. So to really help them and stimulate them on the path to proving something or conjecturing something, we actually further interrogate this pre-trained machine learning model. As you'll see, we use very simple interrogation techniques based on which we can directly give suggestions to the mathematician on where they should look at for a possible conjecture or proof. And hopefully, with these two kinds of hints, the mathematician can use enough context to try to conjecture some new candidate function, which might then lead them back to the process of regenerating the data with this new knowledge, and the cycle kind of repeats, rinse and repeat, on, until the mathematician feels confident enough to go ahead and prove the theorem. So this is kind of the general pipeline, and as you can see, these three steps in the middle can be done by computers. The main steps of conjecturing and proving are still left to the mathematician. So this is very important. And we don't claim to be the first group ever to use computers or computation in the pursuit of mathematical pattern discovery. In fact, I'd say it dates back at least to the time of Legendre, who, for his work on the prime number theorem, basically manually studied prime tables and discovered that there's a regularity in the prime numbers, right? And when computation became more available in the 1950s and so on, we had also theorems that were powered, or conjectures that were powered by computation. Maybe one of the most famous examples is the BSD conjecture, which is one of the Millennium Prize problems from Birch and Swinnerton Dyer, which used the computer to compute a bunch of examples, but then they still manually studied those examples to come up with an interesting pattern. So what we tried to do here is actually use computers for both of these steps. So we could use them to generate our examples for our data, but then we also use computers through the use of machine learning and saliency analysis to try to also detect patterns inside that data and hint to the mathematician where they should look as they set out to prove or conjecture something. Okay, so as I said at the beginning, mathematicians were very skeptical that this would influence many areas of their work. But we actually have, the reason why I'm here, standing here and talking to you about this, is that we actually have been successful. at using this blueprint to make impacts in 2 distinct areas of mathematics in collaboration with top mathematicians. And the significance of our result has been recognized by the journal Nature, where some months ago we have been on the cover. And maybe more importantly than that, I think some of the comments we got from the reviewers, who were professional mathematicians in those areas that we contributed to, were quite telling. So the mathematician reviewers said, this paper marks the beginning of a new phase in use of computers in mathematical research. They cannot imagine a mathematician not using these methods when they are available, because otherwise they would progress much more slowly. And specifically, the experts in the 2 areas we submitted to both said that our individual mathematical contributions would be sufficiently strong to be publishable in a top journal in the area. And we actually just recently got reviewer comments from one of those separate mathematical submissions, and indeed we are very close to getting at least one of these papers published in a top mathematical journal. So within this one paper, talking about the use of AI to help mathematicians, we have at least 2 papers worth of top-tier mathematical content. And specifically, the 2 areas that we tried to support with this blueprint are knot theory and representation theory. I'll be telling you about our individual efforts in both of those shortly. I will just here quickly say that the knot theory work was done together with Mark Lackenby and Andras Juhas from the University of Oxford. And the representation theory work was done together with Jordi Williamson, who is a representation theorist at the University of Sydney. And for those of you who are more experts in these 2 areas and you'd like to know more about the mathematical specifics of what we did, we put both of those individual math papers up on the archive if you'd like to check them out and see what we have done. But what I'm going to focus on for this talk today is to tell you more about how we used machine learning to assist those problems and how our assistance proved helpful. So there will not be a lot of discussion about the maths itself beyond what is necessary to just understand the problem on a high level. So without further ado, let's get started with the knot theory example. This is an example that's good to show first, partly because the intervention of the machine learning model was very simple, to the point where anyone who's done like a rudimentary course in machine learning could understand what we've done here. And it's also one that I've been significantly less involved. So in this particular case, I'm not on the mathematical paper that was submitted. So in this case, it's the work of Alex and Nenad from DeepMind, along with Andras and Mark from Oxford. OK, so as the name implies, in knot theory, we are studying knots, which, as you might know, are these closed loops embedded in 3 dimensions. They feel a lot like the usual knots you might encounter in the real world, with the extra constraint that the loop must close in and of itself. And these are very fascinating objects, and you can study them from various perspectives. Because the knot basically crosses itself in many places, you can think of a sort of algebra of those crossings. So there's a way to look at the knot algebraically. But also, because they're an object embedded in 3 dimensions, you can also study them from a geometric perspective and study their topological properties. And for a very long time, it was basically not known if there exists a connection between the algebra and the geometry of a knot. This was a long-standing missing connection. And our co-authors believed that there might be some connection, and we wanted to use machine learning to investigate this connection. So basically, just following the blueprint I showed you at the beginning, we have access to a knot, and from that knot we can extract some geometric properties, the geometric invariance, and we can also extract some invariants that come from the algebraic or quantum views. And our question then was to try to relate the 2 together, as you might expect, by fitting a machine learning model to take one and predict the other. That was the basic idea. To give you a feel for what this data looks like, this is a typical kind of knot table data that you can get for these invariants. So here are just 3 example knots on the left, and the geometric invariants here and the algebraic invariants here. It is not particularly important to know what these are, especially if you're not an expert in topology. What is important is that these data come in all kinds of shapes, sizes, and formats. So you have things like real numbers, you have complex numbers, integers, and you even have polynomials, which we can represent as lists of coefficients. Okay? Now, what is the easiest kind of machine learning problem you might want to start in terms of how easy it is to optimize in a well-defined metric and so on? Well, that's usually a classification problem, right? Regression is typically a bit more tricky to do, especially if it can grow unbounded. So here we had a very convenient algebraic invariant, the signature, which was an integer, and therefore could be fit as a classification target. So that's exactly what we did. We trained the multi-layer perceptron model to take all of these geometric invariants as input. and predict the signature and an integer quantity at the output as a classification problem. So that's it. We just took your standard off-the-shelf multilayer perceptron, we trained it to predict signature from everything geometric, and it was really good. The R² of the predictions we were getting was about 0.94. So this was very, very encouraging for our math collaborators that, hang on, there might actually be a proper connection between these two ways of looking at the knot, because we can predict the signature very well from all the geometric inputs. But that in and of itself isn't enough to go ahead and conjecture something, because we haven't told them anything about what is it about the geometry that makes the signature well predicted. So we set out to do a very simple saliency analysis, like what are the simplest ways you can inspect what a neural network is looking at. You can check which of the inputs give the most gradient, right, to the prediction. Those are the most important ones. And it turns out when you sort all of these geometric properties by how much gradient they give to the output prediction, you get something that's very telling at the very beginning, right? There's this group of 3 geometric properties, the meridional and the longitudinal translation, that seem to be so much more important than everything else. Okay, so what did we do? We took this plot, we came to Mark and Andras, and we told them, hey, these 3 properties are likely to be very, very important for your connection, right? And what they did then is they thought about it for a second, and they realized that you can define a quantity using these 2 translations, which they call the natural slope, which was obscure enough not to ever be put in an actual knot table software, but it proved a very interesting nonlinear combination of these 2 properties. And from this slope, like if you just plot the slope versus the signature, you get something very, very telling, right? Like it doesn't take an advanced degree in mathematics to see what's going on here. You just look at the axis of the 2 things, and you can basically tell that there's a relationship between 2 times the signature and the slope, right? So that's probably what our conjecture is going to look like. And now the only thing left to do is to bound how much can you deviate from this linear fit. So after some studying on the knots that we had in our data set, our collaborators were able to come up with the first version of the signature slope conjecture. So 2 times the signature minus the slope is a very accurate approximation up to the square root of the knots volume. Okay, so that was the first assumption. It worked for all the knots we had in our initial data set. However, well, as you might expect, the distribution matters, and if you just generate knots at random, you're likely to miss the knots that are very interesting for what might break this theory. And in fact, it turns out that when we really tried to break this theory by generating super twisted braided knots, we could actually come up with a counterexample that completely breaks this initial estimate. Like it wasn't possible to make it work with simple fixing. Okay. So this meant we hit a bit of a wall, but what we thought really what this means is that maybe we use just 2 quantities from the input. Maybe there are more quantities that are important, just a bit less important. So they might feature in this error term, for example. So we went back to our plot that we had before, and what you can notice is when you take these 3 quantities away and you look at everything else, they're not that important, but these 3 quantities then stand out as being significantly more important than everything else. So the short geodesic distance, the injectivity radius, and the cusp volume. So we gave these 3 quantities to the mathematicians, saying one of these 3 might probably be enough to patch your conjecture. And actually, when they took that information and they studied the geometric properties a bit more, they were able to come up with a patched formula where the injectivity radius features in the error term. And this, they were actually able to prove. So this is a theorem that we have now proven. And just in case you were thinking we got lucky with the injectivity radius, they were subsequently also able to prove theorems with one of the other quantities we told them were important too. So they were able to make a deep connection for the first time from the geometric structure of the knot, its slope, volume, and injectivity radius, to an algebraic quantity, which is the signature. And this, if you look at the cover of our Nature paper, this formula, this theorem is highlighted in like white lights and kind of showcased on the intersection between machine and graph paper. Okay, so this hopefully gives you an idea how even with simple interventions, we're able to make measurable, interesting progress in pure mathematics. But now I want to tell you more about the second project on representation theory, which has much more complicated objects than just simple flat observations you'd feed into an MLP. And also, it's a project where I was substantially more involved. I was actually the lead of the modeling in this particular case because it relied on graph neural networks, which is my expertise. So together with Charles Blundell, Lars Boosting, and Alex Davies on the DeepMind side, and Jordi Williamson from the University of Sydney, we set out to try to settle the combinatorial invariance conjecture, which is one of the longest standing unsolved problems in representation theory. Okay. Now, obviously, because I have to introduce the problem in a way in the time constraints that I have, I won't be able to tell you everything that happened throughout development, and I'll kind of streamline the theory that's necessary to understand what was going on. But one thing that's important to note in terms of what the interaction looked like, we from DeepMind really didn't know anything about representation theory, and Jordi did not know much about machine learning. So a lot of our initial encounters were just 2-hour deep dives and lectures so that we could all get on the same page and understand our terms in a way that's commonly acceptable. So that's how it went, that's how it was at the beginning, and most of the machine learning we've done in the middle was very helpful to derive the final results. So I'll show you some machine learning results here. What's important to note is they're greatly not cherry-picked. Like basically, I will show you all the experiments that we needed to do on our path to making this result possible. So this is just a few snapshots from just the amazing amount of effort Jordi put in to explain to us what these different objects are, the different algorithms you can do over them, and also defining a lot of terms in a way that for us will be more acceptable. So that was just, to show you how that initial stage went. Now I'm ready to actually dive into the theory and tell you about the problem we're trying to solve. So we're studying symmetry groups, should be probably familiar to most of you here. They're groups of transformations that leave the underlying object unchanged. And specifically, what I want you to focus on throughout this part of the talk is permutation groups. So permuting a collection of objects changes the way you see it, but it doesn't change the underlying parts of that object. So you have A, B, C, D, E, you permute those objects in some way, that's still the same set, they just look different to you. And we can conveniently numerically code these permutations like 3, 2, 4, 1, 5, which tells you exactly where each element ends up after being permuted. And the permutation groups are also the essence behind models like graph neural networks. So they were also it was quite interesting to study them in this light for myself as well. Now, specifically in this domain, we're going to look at a collection of symmetry groups known as Coxeter groups. And Coxeter groups, in a nutshell, can be fully described in terms of a subset of those transformations, which are known as reflections. And for the specific case of permutation groups, the reflections are the single swaps. So swapping 2 elements in a sequence, and that's all. So if you say have the 4-element permutation group, also known as S4, there are exactly 6 reflections. So these 6 permutations swap 2 elements and leave everything else the way it is. Okay. Now, additionally, a group can have a set of generators, or in this case known as simple reflections, which are just a collection of these symmetries from which you can recover the entire group by composing. And this is actually a foundation behind many sorting algorithms. For permutation groups, you can generate the whole group by just swapping adjacent elements. So 2, 1, 3, 4, 1, 3, 2, 4, and 1, 2, 4, 3. Transformations that swap just adjacent elements. You can arrange the sequence in any way by just composing those. And we call those simple reflections for the permutation group. Okay. Now when I have introduced all of these parts, I can talk to you about how we can represent these Coxeter groups as directed graphs. That will be one of the key objects we're going to be studying. So what we do is we think of each permutation as a node in a graph, which we will later be known as labeled Bruja graph. And okay, we have nodes, the permutations, and we want to draw edges between them. So we draw an edge between 2 permutations if you can get from one to the other by performing a reflection, so by performing a swap of 2 elements. But okay, this graph is still undirected because if I can go from A to B, I can also go from B to A by performing that same swap again. So we need to find a way to make the graph directed, and this is how we do it, in an inductive way. We put the identity permutation at the bottom of the graph. We put all the permutations reachable from the identity by a simple reflection, so adjacent swaps, on the first level. And then we proceed inductively by using these simple reflections. And this gives us a height for every single node, and we can orient all the edges to point to the higher node. Okay? So this now gives us what we know as the labeled Bruja graph, and here's one example of what it looks like for the 4-element permutation group. So you see here 1, 2, 3, 4 at the bottom. You see the 3 adjacent swaps from there on the first level, and then so on, the second level, and so on. You have solid edges, which correspond to these simple swaps, and you also have dashed edges, which correspond to non-simple swaps that allow you to jump further levels in this graph. Okay? So this is the first main object that we will be studying in this particular case. And now let's introduce the main star of the event, the combinatorial invariance conjecture. We'll start by taking any two elements in the Coxeter group, so any two permutations in the permutation group, or the two nodes in the graph I just defined. We can define two objects from these two permutations. The first one, called the Bruja interval, is you take that graph I just showed you, you look at all the paths from one permutation to another, and you drop all of this nice labeling information. So you no longer know which node corresponds to which permutation, you don't know which edge is dashed or solid, and these kinds of things, right? You just have the isomorphism class of that graph, that's all. Okay? And then you can also define a Kazhdan-Lusztig polynomial, which conversely is a bit easier to work with, but much harder to properly define. So I won't say much other than it's a polynomial with integer coefficients. Okay? And one important thing to note here is that this Bruja interval, as I said, is unlabeled. So we don't know which node or edge corresponds to what. We just have the graph structure. And it's been a long-standing 50-year-old conjecture by Lusztig and Dyer that these two objects, the graph and the polynomial, are fundamentally related. That is, that you can compute the polynomial from the graph. Okay? And this is the combinatorial invariance conjecture. For 50 years, it stood basically without any really serious attack. And if you give me a moment, I'd like to show you why I believe this conjecture withstood attack for so long. So we want to find maps from these graph structures to polynomials with integer coefficients. That's the main problem. And the reason why it's so hard is because patterns in the polynomial emerge quite late by the time these graphs are really big. So here in the 4-element permutation group I showed you before, all of the polynomials for all the subgraphs are 1, except for this one called the crown. For the crown, you get 1 plus q. So this is the simplest possible example for which a q appears. And already the structure is a little bit complicated. Now you might be asking, of course, this polynomial can go to any power of q. So how complicated does this graph get before I get to q squared? It gets this complicated. This is the smallest graph for which there's a q squared in the polynomial, right? And as Jordi dutifully remarks here, this is one of the easiest examples. But already at this point, it's a bit tricky for a mathematician to look at this and say anything about what's the structure inside these things, right? So this is, in my opinion, the reason why there hasn't been a lot of progress. We didn't have tools to gaze into these graphs and tell you what are the things that are most important, because they get so complicated before the polynomial gets even mildly complicated. Okay, so we want to train a machine learning model to predict the polynomial coefficients from this graph. So there's this graph structure. Once again, all the data has been dropped. You just have the graph structure, nothing else. And the polynomial coefficients as the prediction target. Because they're integers, we can do classification problem once again. And just to show you, this is one of the simplest examples where you have q and q squared at the same time. I'm not even going to bother showing you a q cubed example. Like, this is already way too tricky. Okay, so which model to use? Well, the inputs are graphs and also algorithms that can compute these polynomials if you gave access to all that privileged information we discarded, like what node corresponds to what. Yes?
Sorry, the graphs you showed,
Those are the subgraphs, yes.
Okay, so they're hard to
Yes, exactly. I mean, it's a permutation group of n elements as n factorial permutations, right? So there's a lot of nodes in there. Okay. So basically, we knew that there existed algorithms that will compute this if you give them access to all that privileged information we discarded. And those algorithms, the equations of them felt a lot like graph neural networks, which is a model that I'm an expert on. So basically, you compute something for all the neighbors, you sum it up, and then you apply some function that feels a lot like a ReLU activation. So to us, this meant we should use a graph neural network for this. And we can treat it as a graph classification task. So take this entire graph at the input, embed it using a graph neural network, and then predict an integer at the output for a particular power of q. What's the coefficient? Okay. So we tried that. We built a data set of all the interesting intervals up to the 9-element permutation group, where 9 factorial already starts to bite you a little bit. And after training the GNN, well, these are the initial performances we got for the different powers of q. And As you can see, it was quite performant, like much better than taking the majority class or something like that. So this already gave a lot of encouragement to Jordi that, okay, there could be a formula hidden inside here, but it wasn't completely worked out, right? There were these coefficients that weren't predicted so accurately, like 63% or something. So we went back to the drawing board and we tried to help Jordi see inside these graphs by asking ourselves, what did this GNN learn to do? And, well, we can use the same gradient saliency method we used before to highlight the nodes and edges that got the highest gradient contribution to the output. And this gives us subgraphs like these. To me, and probably to many of you, these graphs look useless. But we thought we'd try anyway. We sent a bunch of these graphs to Jordi, and he stared at them for 2 weeks. It was very hard. And he was actually able to tell apart the signal from the noise. Like, yeah, this guy is something else. But basically, he was able to figure out that there exists an interesting structure inside these graphs called diamonds. So something taking the root node and basically these diamond-like structures of the neighboring nodes. He found that that appeared quite often in the subgraphs we showed him. And there was a lot of related research on these diamonds and the related idea of dihedral intervals. So he hypothesized, okay, these things could be quite important for the prediction that we want to do. So we did an iterative step. Let's compute a bunch of these diamond properties, feed them as extra features for the graph neural network, and let's see how well it performs then. Yep. Like basically at this point, we were saying, okay, there's definitely something here. We're going to have a conjecture for sure, right? And Jordi also thought, okay, we knew these dihedral intervals were pretty important at this point since they boosted the accuracy by such a huge amount. Now, the last important piece of the puzzle, which allowed Jordi to complete the picture and actually propose some conjecture, is we could study of all those edges that got selected, because we know those edges correspond to swaps, right? We can check which elements those edges tend to swap. And the heat map we got was very telling. You can see how it tended to prefer swapping element 0 and element 8, right? Those were kind of the hottest elements of this heat map, all right? And this insight that the most important edges were extremal reflections, things that swap things that are far away in the sequence, led Jordi to complete the theory that we needed. And in fact, one of the reviewers commented in the Nature paper that the insight that extremal reflections seem to be crucial is what they would have expected only from a handful of great world experts in representation theory, and is such a human suggestion that it gave them goosebumps. I quote directly from the review. And basically, you know, this was a completely machine-generated insight, like this heat map, from the saliency analysis. Yes. Yes, but this was specifically for the extremal reflections, not the dihedral intervals. Yeah. Yeah. Okay, so based on these two together, the dihedral intervals and the extremal reflections, Jordi was able to conjecture about this hypercube decomposition, where you find a subgraph here which looks a bit like a hypercube in n dimensions, and then an inductive piece which is a coset in a smaller group, from which he conjectured we can compute this KL polynomial inductively. And in fact, he was able to prove a theorem that for every Bruja interval that we have, there is going to be a canonical hypercube decomposition into these two parts that lets you compute the KL polynomial as the sum of two terms. And what he said is that the inductive term is something very well familiar to experts in representation theory. This hypercube part was completely novel, and the suggestion came partly from the machine, so it was very insightful in that regard. And we then wanted to decide, because this doesn't settle the conjecture yet, right? Like, it says there exists one decomposition. It doesn't tell you how to find it. So we wanted to try a bunch of these decompositions to see how often it gets it wrong. And for all the intervals we were able to generate, we haven't found a counterexample. So we actually have a conjecture in our paper saying that no matter what hypercube decomposition you choose, this formula will work. And Jordi put some suggestions in the paper for how you might go ahead and prove it if you're a representation theorist and you're interested in working with these kinds of things. So just a few takeaways. I realize I'm breaking my time limit a little bit. So what I think are the key observations in this work is that I think even simple machine learning interventions, train an MLP, take the saliency of the inputs, can have a large impact in mathematics. And mathematicians are not just theorem provers. They take this kind of insight from the model and they can use it in creative ways. And the method seems particularly appropriate when you want to do this kind of relating of x to y, and you can generate a reasonably large data set of structures, especially if those structures get too complicated before the mathematician can really observe what's going on. And which areas would we need to improve of machine learning, or maybe even quantum machine learning, to make even more usability of this method? We used very simple explainability techniques and got very lucky. I think to really make this accessible to all of mathematicians, we need to really work on our explainability methods. And further, because mathematical objects can get more complicated in graphs, they can have funky topological structures and symmetry groups, we should work more on geometric deep learning and try to build models that are more suited for those architectures. And lastly, because of the effect of these simple interventions, many of you are mathematicians, many of you might know good mathematicians. Just reach out to a mathematician near you and try to see how you can help them with the problems that they're facing. We put all of our source code open on GitHub, and you can reproduce all of our experiments for both representation theory and knot theory without requiring any GPU farm. You just need one GPU to reproduce everything. And lastly, the account I gave today is the account of a machine learning scientist, but obviously we worked for mathematicians, and it's insightful to know how it felt for them. Jordi Williamson wrote this fantastic piece for The Conversation where he told about how it felt from the mathematician's point of view, and I think there's a lot of insight there that can be interesting even if you don't want to know just about the mathematician's point of view. So I highly recommend reading this particular piece. And that was my last slide. Thank you so much. I hope you found it interesting, and I'd like to thank all my collaborators once again and for inviting me to this event. So that's a very interesting point. We are thinking about things in the direction of P versus NP, and we believe some of the ideas here, like searching for interesting gadgets and problems, might be helpful from a complexity theory standpoint. But yeah, like I definitely feel like there is something there potentially. We haven't thought that deeply about it yet, but that's a great point. Yeah, oh, sorry. Yeah.
Thanks for a great talk. So in the first part about the knot theory stuff, am I right in saying that the way it kind of worked was you kind of classify and found features that were highly predictive of the outcome and gave those features to the mathematicians, and they devised formulas that could relate them and the deviation from them and so on and so forth. Do you think things like symbolic regression might be able to help in kind of positing certain functions or equations that might be then helpful for mathematicians to explore?
Right. So the question was, did we do a back and forth with mathematicians where we gave them interesting inputs to a machine learning model and then they went away and derived the conjectures by themselves? Yes, this is what happened. And then the follow-up to the question was, does this mean we could use symbolic regression to automatically discover these formulae? Yes and no. So there have been some successful works from folks at Princeton that use this kind of approach to rediscover the laws of gravity, for example, from a lot of n-body simulation observations. So you can reconstruct the algebraic rule sometimes. But the reason why I say no is because we tried symbolic regression quite a bit, especially for the second problem in this deck, and we were unsuccessful. Like we found some interesting algebraic rules, but they all failed in very subtle ways. So, yeah.
Thank you for presenting very interesting math results. But going to your title, which is not plain math results, AI math, and trying to put it in the context of the previous talks about ambiguity, mathematicians would battle against ambiguity by defining the two terms which we connected, AI and math. And both of them can be defined, John McCarthy would define AI in a way which would assure that almost every collaboration between mathematicians and computer scientists would be AI. And the other way around, it's possible to define the two in such a way that there is no possibility of. So how do we define these two things to assure the flow of information between the two to result in creativity?
Yeah, this is a very important point, and I don't have good insights myself, but I can say what Jordi, for example, made of some of this when we asked him to give some analogies. He likes the analogy of a pocket calculator. Like if we were able to give Gauss a pocket calculator, they would be able to derive some of the things they were working on much more efficiently. So it's a tool that you can invoke when you want to hunt for patterns in complicated objects, and then you can use those patterns to, proceed with the regular work of mathematicians, for now. In the future, we might see fusion with things like theorem proving and so on that might actually try to also help you do the proof part of the work. But yeah, honestly, I feel like supervised learning is way closer and within reach to being applied in this way, as we managed to successfully do it here, than theorem proving. But the future could definitely, the future might lead to an expansion of what AI really means as a tool. But currently, I see it as a pattern detecting tool inside mathematical objects. Yeah.
Okay, well, thank you so much for your talk. And well, let's thank the speaker.
Thank you.
Okay, well, the second talk, we welcome Kieran Gillen-Lee from Spotify in University College London, and we're going to hear about interfactual reasoning and what it's good for.
Thanks very much. Can everybody hear me okay? Perfect. Well, hello everybody. My name is Kieran. Hopefully I'm going to give a talk at least a quarter as interesting as the last one, which I really enjoyed. So today I'm going to talk about counterfactual interesting, why it's interesting, what it's good for, how we should do it. And along the way, I'm going to really try and ground the discussion by giving lots of practical examples, real-world cases where we need to use this type of reasoning and so forth. Okay, so along that line, let's start with a fun example. So here is a prominent anti-vaxxer taking to Twitter in 2021, and he's showing some data taken from the Office of National Statistics in the UK. And what he's plotting is the death rates among people who've been vaccinated versus people who haven't been vaccinated to COVID-19. And you can see a strange pattern start to emerge. The orange line here is the death rate after people have received their second vaccination, and the blue line is no vaccination. So a strange thing is happening. There's an increase in the death rates among those who've been vaccinated. This seems strange, right? COVID-19 vaccine should protect us from mortality rates from COVID, but the data is saying something completely different. So what's going on here? So he was kind of using this as a way to kind of suggest that perhaps it's not the best policy that governments vaccinate their populations and so forth. So looking at this data, it seems like that seems like a reasonable thing to do. But if we dive a little bit deeper into the data to kind of figure out what's going on, there's a big confounder here, and that's kind of skewing the observed correlations we're seeing and kind of obscuring the underlying causal relationships. So what's actually going on is the average unvaccinated person is much younger than the average vaccinated person, because older people, they were allowed to get their vaccine earlier and so forth, and they think it's probably more important because perhaps they're more at risk of COVID, so they're more likely to get the vaccine in the first place. So therefore, people who've been unvaccinated have a lower mortality rate just because they're younger, right? They're less likely to die from other causes than COVID and so forth. So any benefit from the vaccines is swamped by the increase in mortality as we age. So age here is a confounder. It's influencing both whether you get vaccinated and also what the impact of that vaccination is on your mortality, for instance. So the question we have to ask now is, what's the actual causal effect of being vaccinated on your mortality rate? Because we've done all of these randomized control trials that have showed that vaccines reduce mortality and so forth. So clearly there's a proper causal relationship here, that vaccines are good for us, but the data is kind of telling us something different. But when you control for age, you hold age fixed so that in both vaccinated and unvaccinated cohorts there's an equal distribution over age, then indeed the correlation goes back to what we would expect given what we've seen in our randomized control trials. So after this came out, the Office of National Statistics had to put a big disclaimer on their website where you can go and look at the mortality rates from COVID and so forth, highlighting this kind of bias that's being brought in by age and suggesting people should reason about it, in some appropriate fashion. So the kind of take home from this is that any action or policy change based on these correlations, such as whether we should vaccinate a population, would not have increased patient survival. So relying on correlations extracted from observational data can lead to embarrassing, costly, or in this case, dangerous mistakes. So to overcome this, what we need to do is reason about cause and effect rather than just looking at raw correlation. Cool. So how do we do this? Well, the gold standard is usually running in what in industry is called an A/B test, but in the kind of medical literature, we call these a randomized control trial. So when we do this, we kind of randomize whether you receive treatment or not, so any kind of influence of a confounding variable is removed because it is random allocation. So we can truly reason about cause and effect in these situations. But there's lots of cases where we can't run A/B tests or randomized control trials. For instance, they could be too damaging to the user experience. They could be technically too hard to implement. So if I want to figure out if app bugs or crashes on your app cause users to leave that app service, then I can't really do a randomized control trial where I force some users' apps to crash, because that just might annoy them a lot. Or I want to figure out in the context of Spotify, does podcast consumption really cause users to stay around more, or is it some combination of other things? Again, to do a randomized control trial here, I'd have to remove all podcast content from Spotify, which probably would have knock-on consequences and probably is a difficult thing to convince people that is the right thing to do. And on the kind of more physics side of things, if I want to figure out if the moon is causing the tides on Earth to change or vice versa, I can't really go out and move the moon around. Well, in principle, I could stick some rockets on it, but it's not technologically feasible to do these things. So lots of times we can't do this kind of perfect gold standard way to figure out cause and effect relationships. So that's where causal inference comes in. And so, it's a field that has a bunch of tools that, allows us to quantify cause and effect given certain assumptions. And even when we can't do these A/B tests, so it's super powerful. And so what I'm going to talk about today is what a causal model is, what we can do with it, but a focus on a very specific type of inference we can do with causal models. So first, let's kind of define what a causal model is, so we're all on the same page. And then I'll talk about the different types of inference we can do when we have access to such models. So the kind of basic idea is we have some observed terms. So here, in this case, the observed terms are the kind of orange or yellow nodes. And we also have some sort of noise terms telling us, factors that are influencing these observed things that are outside of our model. So they're the green things in this kind of thing here. And the general assumption is that noise terms are kind of distributed according to some unknown latent distribution, and the observed terms are a deterministic function of the parents of that node in the graph together with these unobserved noise terms. So you might say, okay, well, this is strange. Why is there this underlying determinism in my graph? Surely these kind of causal graphical models, sometimes people refer to them as Bayesian networks, they assign joint distributions across these observed nodes, but you're telling me there's deterministic functions underlying this. This is kind of strange. But the point is that we don't know what the distribution of the latent noise terms is, so that uncertainty then propagates through these deterministic function to give us uncertainty about the observed nodes and so forth. So together, all this information jointly generates, joint and conditional distributions over the observed nodes. So we have all this structure, we have this joint distributions and the functions underlying them. And the question is, when we have this, what can we do with it? So Pearl, who's one of the kind of fathers of causal inference in the computer science community, kind of defined what he called a causal hierarchy. So 3 things that we can do with a causal model. So at the first layer, what we can do is talk about standard Bayesian style inference,
asking what the joint probability of certain outcomes might be, the conditional probabilities and so forth. Then the next level is what he calls interventions. So these are things that talk about how to kind of simulate an A/B test using, let's say, just observational data. And then at the very top of the hierarchy, what Pearl defined as are counterfactual, so ways that he said are something akin to imagination. So I'm going to talk a little bit more about these in detail to give you some examples. So the kind of standard example in causal inference is the question, does smoking cause lung cancer? So in lots of cases, there might be unobserved factors, like in our vaccine example, that could predispose people to smoking, but also to getting cancer in the first place. So it could be some underlying genetic precondition and so forth, or various other kind of factors. And at the first level, what we can do is ask, okay, given that I've observed somebody smokes, what's the probability that they have cancer? So they're the types of questions I can talk here. The next level, interventions, is kind of simulating randomized control trials that we talked about a few slides ago. And this is a kind of crucial bit of Pearl's kind of formalism, that he introduces this thing called a do operator. So it's meant to kind of formalize this idea of reaching into my model and forcing some variable to take a certain value. So this is kind of what happens in a randomized control trial. I'm forcing some randomly selected group of people to smoke, forcing another subset to not smoke, and this do operator, this kind of do notation here, is what's telling me that. So the difference between this and the previous kind of notion of just doing observational inference is that I've observed someone smoking in the previous one, and that could be due to other factors such as, genetic predispositions and so forth. But in this case, I'm observing the fact that I intervened and forced them to smoke, so I'm acting in the world. And this is kind of how I should think about what randomized control trials are. And then at the last level are these counterfactual things. So they really are kind of truly what-if types of questions. And it's slightly different, the interventions on the previous slide. And it's kind of slightly, it sounds quite complicated. If we look at this distribution here, we see cancer, this C variable, appear on both sides of the conditioning symbol, so it seems very strange. But actually, when you unpack this, it's quite intuitive. So what I've done is I'm saying, okay, I've observed that the person has cancer, and I want to say, in that context, if I had forced them to not smoke, I want to then ask, what's the distribution over them not having cancer? So cancer being false in this kind of situation here. And this seems like a kind of quite a complicated expression to try and estimate what's going on. Cancer appears on both sides. How do I do this? So Pearl introduced a nice 3-step inference procedure to kind of figure out how we should estimate these types of counterfactuals. So the first step is what he called abduction. So it's saying, okay, I've observed some evidence in the real world. So in this case, I'm looking at, given I've observed someone smokes and they have cancer, I've observed that in the real world. So now I'm updating my knowledge about any latent distribution, so the likelihood that they have a gene that might predispose them to smoking and kind of so forth. So I'm updating my knowledge about that. In that context, I then apply this do operator. I reach into my model and I force the subject to not smoke. And then what I want to do is, in this new model where I've done this intervention, this graph surgery, I take this new distribution, this updated distribution over my latent, and then I kind of feed forward. So I sample from that and I kind of feed forward and predict what the distribution over having cancer or not is in this kind of updated model. And so this kind of procedure tells us how we can estimate those strange counterfactual looking things at the top. So to kind of give a quick illustrative example of what's going on here, here's a kind of nice case from kind of medicine. So what I've got here is this 3-layer network. The top, I have a risk factor about someone being overweight. The next layer, I have possible diseases that risk factor causes. And then at the last level, I have kind of symptoms. So symptoms that are caused by the diseases that are linked to the kind of risk factor and so forth. So what I want to ask here is, given I've observed a patient has these symptoms, they're present in the person at a given time, I want to now say, what would have happened to them? How likely would it be that they're still there had I intervened and cured a specific disease, or reached in and turned off a disease, for lack of a better term. So the diseases here, I'm assuming, are just binary variables that tell me if that disease is present or not. Okay, so let's use Pearl's 3-step procedure to do this. So the first step is I've observed this evidence, and now I want to abduct, so update the kind of model, the parameters of my model given that I've observed that. And then I want to do this action. So I want to reach into my model and cure a specific disease. So I kind of sever any incoming reasons why a specific disease, in this case angina, might be there, turn it off. And then in this context, I want to feed forward and kind of figure out what's going on. So I kind of predict and pull everything down to what's going on. So that's the kind of process of how one can compute these counterfactuals. So I've said that we have this nice 3-layer hierarchy. And at the middle layer, I've said these things, these interventions simulate randomized control trials. And I said at the start that randomized control trials are these kind of gold standard for doing causal inference. They're what we should try and figure out. But I've never said anything about counterfactuals being useful. And actually, when I was reading the kind of literature on this, I couldn't find any key examples, real-world cases where counterfactual reasoning was super important for the outcome, and I couldn't have done the same type of reasoning by just talking about interventions and so forth. So what I want to talk about today is there any context in which counterfactuals can offer some form of advantage in reasoning over observations or interventions? And so the way I'm going to do this is I'm going to explore that example I just gave about medical diagnosis and kind of see, do counterfactual reasoning play a role in kind of how we should formalize this from a kind of machine perspective. Okay, so before I kind of dive into that, I'm going to talk a bit about the disease model that we're going to use and do counterfactual reasoning on top of. So here we have this three-layer kind of network, risk factors, diseases, symptoms, and so forth. In the kind of context of the next few slides, we're going to assume that we have this structure given to us. So some medical professionals or epidemiologists and so forth might have gone into the literature, taken their domain knowledge and said, okay, I know this risk factor causes this disease, but not this other disease. I know this disease causes this symptom, but not this other symptom. So they input this kind of graphical structure there. We then go and kind of look at the population and say, how likely are these risk factors among the population? How likely are these diseases? And kind of so forth. So we have both the graphical structure, the orientation of the arrows, as well as kind of joint distributions and conditional distributions over this. So we're taking that as a given. And the question is, if I want to kind of diagnose a patient, how should I do it? So what's going to happen is I have this big model that's been given to me by experts. A patient comes in, we kind of take from them what symptoms are present. You know, did they have a cough? Did they have a headache? Various sort of things like this. I then input these into my model, and what I want to do is infer the disease that's causing these symptoms. So this problem goes back to the kind of mid-'80s where, you know, people were trying to make this an automated process. Given a model, how do I figure out what disease is kind of underlying or could explain the symptoms? And the standard way that they do it is just using posterior inference. So they say, given that a certain set of symptoms are present, and moreover, I know this specific patient has these risk factors, what's the probability that a certain disease is true in this case or is likely? And then I can just say, okay, looking at all the diseases in my model, which one is most likely given all this evidence? So that's the kind of standard way of doing it. The way I'm going to propose today is instead formulated in terms of counterfactual inference. So what I'm going to say is, given that I've observed a certain set of symptoms are there and some risk factors, and now if I reached into my model and set a disease to be off, so I cure a hypothetical disease, I want to ask, in that new context, is it likely that the symptoms are cured? And if not, then I'm going to say, okay, this disease is not causing your symptoms. But if that has a high probability, I'm going to say, okay, this disease is a good candidate for causing these symptoms, and it explains them really well. So why might we expect the counterfactual approach to work better than the standard kind of posterior ranking approach? Well, if I go back to this graph I had a little while ago, and I look at what happens here. So I observe certain symptoms, shortness of breath, chest pain, and so forth. I then I do a standard Bayesian update my model. In this case, what we can see is if those things are there, then it's highly likely that the patient belongs to a population that was overweight. And moreover, if they belong to such a population with some high likelihood, they have diabetes. Again, this is a hypothetical example. And in this case, diabetes does not cause the symptoms, right? It has no causal link here. But yet, it's very likely, given the evidence, right, that this person belongs to this subpopulation and so forth. But in this case, diabetes would be a bad explanation of my symptoms because there's no causal link. If I reached in and somehow cured the patient's diabetes, maybe giving them insulin and so forth, it would have no effect on their symptoms. So a doctor would never do something like this, right? Because they want to find a thing that if they reached in and provided treatment, they could reduce a patient's symptoms and so forth. Whereas in this case, that wouldn't happen. But the counterfactual case would account for this, right? Because if I updated my knowledge, I see diabetes is quite likely, but now I reach in and I cure diabetes, it's going to have no effect on the symptoms. So it would be a bad explanation in this case. But something like angina, for instance, has this kind of strong causal link, and so it would have a high probability in the counterfactual sense, and so would be proposed as a good kind of explanation of my symptoms. So that's kind of why we might expect it to work. How do we actually go and test this in the real world? So what we did was we got a kind of panel of doctors, and they compiled about 1,700 medical cases, and these are kind of very similar to what kind of trainee general practitioner doctors are given before they become qualified. They have to go in and kind of they're given a case like this, given some evidence, background on the patient, and they're kind of told, okay, this is the actual disease that this panel of doctors thinks is really likely in this case, and a good doctor would infer this from all the information. That disease is then hidden from the doctors and from our kind of algorithm, and we want to infer from all of this information what the most likely disease is. And then we can kind of score the approach by saying, okay, is this disease that the panel of experts thought was the kind of right disease in this case, is that inferred by the algorithm? And so what we want to do is output a ranked list of diseases. So all of the diseases in our model, let's rank them, how likely they are given all of this evidence, and then we want to compare whether the disease actually on the card is in the top K of this ranked list for all the kind of output ranking of our diseases. And we're going to compare the counterfactual approach to the kind of standard Bayesian updating approach. So the important thing to note is that the underlying disease model here stays fixed, so nothing changes. All that changes is that we're changing the way we do inference on top of this model. Cool. Okay, so you can kind of see here the slight difference as we're kind of increasing K. So we're looking at, okay, the list of diseases, the top disease, top two diseases, and so forth. The causal model using this counterfactual reasoning is getting to the right answer kind of quicker. In a sense, it's always higher up the ranking than it would be for the standard kind of machine learning approach where we're just doing standard Bayesian inference and so forth, which is definitely very nice. The real question then is, if we compare to real doctors and compare their kind of inference capability on the same set of tests, how does the standard Bayesian updating approach compare to the counterfactual approach? So we took 44 doctors who weren't involved in creating these 1,700 kind of cases, and we compared how both algorithms did to how the doctors did. And you can kind of see here on the top, we have this kind of red line. If you're above that red line, the algorithm is doing better. If you're below that red line, the doctors are doing better. The same for the counterfactual here. And you can see that in the counterfactual case, the algorithm is doing much better than the kind of doctors in general. So it's places in the top 25% of doctors, where the standard Bayesian updating approach places in the top 50% of doctors. So still pretty good, but we get this extra boost from reasoning counterfactually, which is pretty cool. And a kind of important thing to kind of note here is that when you look at the kind of bottom left quadrant here, this is a case where doctors found the kind of cases really, really difficult, right? Their accuracy on certain cases was very hard, but in those cases, the algorithm always performed better. So it always kind of was able to outperform the doctor there. But when we went up and found cases that the doctors found were easy, perhaps they see them a lot in their clinical practice and so forth, they were outperforming the algorithm. So that's something kind of interesting to kind of focus on. Perhaps there could be some nice symbiosis between doctors and AI, where for really challenging cases, the kind of algorithm could suggest certain things the doctor could think more about. But in cases where the doctor has seen it a lot, they can just go with their gut, and that's kind of the right thing to do. So that's kind of great. If you're interested in kind of reading more about that, it's up on the kind of archive there and so forth. We got some nice press about this when it came out, which is always good. And so what I kind of asked at the start was whether counterfactual inference is useful for something. So what we've shown there is, at least in the context of medical diagnosis, it was useful, which is fantastic, right? We answered that question. But then the next step is saying, okay, can we generalize this to other types of problems where we might want to reason counterfactually? And the thing I should kind of point out here is that we got this advantage, but in a not very generalizable way. The model that we had constructed, the structure was given to us by experts, but moreover, we kind of imposed a parametric model relating how risk factors cause diseases, how diseases cause symptoms, and so forth. So we can't really generalize this to just saying, give me some raw data, I'm going to train a causal model on it, and then do counterfactual reasoning. We kind of used what's called a noisy OR model in this case, and the reason for that is it's well used in the medical literature. It also kind of tells us that if we have multiple diseases causing the same symptom, if I observe the patient has another disease, it can only make the symptom more likely. It can't reduce the likelihood of the symptom, which makes kind of intuitive sense in the domain of medicine. So the question is, can we answer counterfactual questions from data without the need for these parametric assumptions? Can we do it using sort of fancy neural technologies and so forth, so that we can now kind of scale and apply this in many other domains where we might not know what the underlying functions should kind of look like, where we just have raw data and so forth. The other question is, do we need to, right? Are there cases where it actually would be useful to do this counterfactual reasoning? And then the last question is this even possible? Do we run into any kind of extra problems when we try and do this without the use of a kind of parametric model? Okay, so here is our second motivating example, which is kind of hopefully designed to show that it's useful to reason counterfactually in other contexts. And so here, there was an NGO that kind of went into Africa, and they kind of saw that diarrheal diseases were a leading cause of disease and mortality in the developing world, especially among young children. So to reduce the kind of likelihood of young children getting these diseases in a certain area of Western Kenya, what they did was they went in and they kind of built wells like the one on the kind of top right-hand side here, where you looked at where the kind of local kind of people were going to get drinking water. You set it up so that there wouldn't be kind of mud and bacteria in the water when they're collecting it. And they wanted to see, would this reduce diarrhea? So what they did was they set up a randomized control trial where they selected villages at random, went in, built these kind of wells and so forth, and compared the incidence of these diarrheal diseases in between these kind of two contexts. So they found that spring protection significantly reduced the diarrhea for children under age 3 by about 25%. So that's great. I mean, that seems like a really kind of useful thing to do, help people in the developing world and so forth. So the next question is, should we scale this intervention up? Is it the right thing to do to now go across Africa and reproduce this kind of intervention in all kind of cases where we'd find such kind of water sources and so forth? So it's really expensive to kind of do this. And so most NGOs, they want to make sure that they're allocating resources in some optimal kind of fashion. So they want to figure out, is this the right thing to do? Did we actually see an effect of the spring protection, or was it something else about us perhaps going into a village, educating the people by saying, okay, we're building this well, it's meant to reduce diarrhea, and the reason it does that is it stops kind of bacteria getting into the water. Was it just that educational element, or was it the actual intrinsic thing of protecting the spring itself? So the question that we really need to answer in this case is, how likely is it that the negative outcome was caused by exposure to diarrhea, in the kind of bacteria and so forth, and not something else? So the question that we kind of want to answer is, given a child developed diarrhea after drinking from an unprotected spring, would they have still developed diarrhea had they drank from a protected spring? So it's a counterfactual question. It's precisely one of the ones very similar in structure to what we asked about kind of diagnosis. So it's another case where answering counterfactual questions would be super important for deciding whether to kind of go in, scale its intervention up and provide the right benefit, or whether there's something else we should look at that could be perhaps cheaper to scale up and kind of provide the same level of benefit. Okay, so let's introduce a little bit of notation just so it's easier to kind of talk about these questions. So what I'm going to say is capital Y with this subscript x equal to little case x is the value of y when we intervene with this do operator. So that's the kind of notation I'm going to use for describing this thing. And now we can introduce some sort of new causal questions, which are, for instance, what's reproduced here, which is the probability of necessity. So given I've observed that x is true, so I'm dealing with binary variables x and y. So I want to say, given that I've observed x is 1 and y is 1, and perhaps there's some observed confounding going on here, some sort of context and so forth, so a condition on that as well. I want to ask, in this context, what's the probability that y would be 0 had I intervened and set x to 0? And so this is the probability of necessity, and it really tells us that what the probability of event y would not have occurred without event x occurring, given that x and y did, in fact, occur. So the question that I really want to answer here in the context of this spring kind of case is the following. So given that a person developed diarrhea from drinking from an unprotected spring, what would the likelihood of them still having or not having diarrhea had I protected the spring? So I want to figure out the answer to this specific question here. So here's where we hit our first speed bump. Is it possible to even learn such a thing from data? And so the question we want to ask is if this quantity is identifiable from the type of data we have access to. So given observational data and data from the interventions that have been performed, can we infer what the answer to this counterfactual question is? And what we want to show is that a kind of quantity is identifiable from specific type of data if every model that agrees on that data produces the same value for that quantity. So I want to see that if I can show there are two models that exist that agree on the data I have access to, so the observational data collected from the springs, the interventions that I performed in a randomized control trial, would those two models agree on the counterfactual question I want to ask? Turns out for counterfactuals, the answer is no, you can't always do this. There are certain counterfactuals, even when there isn't unobserved confounders, where you cannot identify them from observational or interventional data. So here's a kind of quick little example. If A and B are just, again, binary variables, the standard basic kind of causal model here is kind of described as follows. So without loss of generality, A to B is the mapping between two bits. So it's a kind of 4-valued function here. So the mapping can either be the identity, a bit flip on A, it can be throw A away and prepare 0, it can be throw A away and prepare 1. And what's going on here is the noise term up there on B tells me which one of these cases it is. So kind of sample from that, conditional on that, it tells me which one of these functions it is. This is the most general type of kind of causal model between 2 bits. And you can kind of see that this model is completely specified by the distribution over my latent variable up here. So if I know what that distribution is, I can tell exactly what the causal model is. And looking at this, U is a 4-valued variable. So a distribution over it has 3 real parameters. You know, it's normalized, so that kind of cuts out 1. So what we want to ask is just from kind of observational data, so conditional distributions between A and B, does that perfectly constrain my causal model? So in the previous thing, I saw that this model had 3 parameters, but the conditional distributions only have 2 parameters. So there's 1 free parameter left that I can use, in a sense, to construct 2 different models that agree on those conditional distributions, but disagree on that last parameter and hence have different counterfactuals. So here's like a specific example, kind of relating these quantities to the parameters of my model, and I can kind of see that for certain counterfactual questions, the way it's related to a parameter, I cannot infer that parameter from just conditional distributions. So there's no way for me to learn this counterfactual distribution from data. So I need to do something else. I need to kind of impose extra constraints in order to learn this kind of quantity. So what we need to do here is add these extra constraints to infer what these counterfactuals are. And so the question we might ask is this actually a problem? Like, will this run into any issues if we're trying to reason about counterfactuals? Or can we just trust any model that reproduces the observations that I've seen? So to kind of give a quick overview of this, we took some data from the German credit data set. So we have an individual's account status and other financial data, as well as whether they were approved for a loan, how risky they might be, and so forth. And from this data, just kind of looking into it, we see, as we would intuitively expect, all else being equal, the better the account status and how much money is in there, the lower the loan risk. So the more likely that the person will be given a loan. So it seems intuitive. If you increase your account status, your likelihood of getting a loan increases. So we want to now ask the counterfactual question, conditioned on an individual having low net worth and the fact their loan was just kind of denied, what would we expect had we increased their net worth in this context? Feels like their loan probability should increase. But what we found when we trained a causal model without any additional constraints is that that wasn't the case. Actually, in this context, when you condition on that information, increasing their net worth reduced the likelihood that they would get a loan. Which seems really counterintuitive and actually wrong in this context, right? Because it's completely not what we would expect given our knowledge of the financial industry and so forth. So the model here actually decreases probability. So this is showing us that unless we impose additional constraints, there are some counterfactuals that are just kind of wrong given the domain knowledge we might have access to. So the kind of main issue here was that the ordering between the interventions, if I increased net worth, it was always the case that the likelihood of loan approval went up. In this case, those interventions, that ordering was flipped in the counterfactual context. And so we might want to ask, what happens if we just enforce that the ordering on interventions is the exact same as the ordering on the counterfactual context? And so we did that. We imposed this kind of definition here. It's kind of just ensuring that the ordering we see when we look at interventions is reproduced in the counterfactual context. And what we showed was that there's an easy way to say, okay, if this is true, you can now find an easy way to enforce your model to learn these types of counterfactuals. So you just ensure that they're monotonic, which is that when you increase the input, all else being equal, the output at least doesn't decrease. So when you enforce this on the functions underlying your causal model, you get kind of nice, interpretable and trustworthy counterfactuals. So in the binary case, this actually uniquely identifies all counterfactuals, which is great. Beyond that, in a kind of the categorical case, we can kind of impose this. It doesn't completely identify the counterfactuals, but it's partially identifies them. And so what we should do is we should say, in this case, we should trust the counterfactuals that the model outputs because the strange, non-intuitive ones have been thrown out. So, what we should also note is that the causal analyst looking at the data should be the one to decide if a certain assumption is reasonable given the domain. So we're not saying this should be true for all causal models, but in lots of contexts, like, the kind of financial industry and also epidemiology, this seems intuitive. So you can then go on and figure out how to train causal models given this extra constraint. So, when you do that, you find that actually you get the correct intuitive probabilities. Given we observe someone had, low net worth and they were denied a loan, we want to ask, in that context, had we increased their net worth, would their likelihood of getting a loan increase? And when we impose these constraints, the answer is yes. So it's great. So it seems trustworthy in this kind of context. We can then go on and kind of figure out how to train a causal model given this extra constraint. So I'll skip over this, but if you're interested, it's in a kind of paper that I'll talk about at the end. And we can now get to the answer to that question that I proposed earlier. Is it the right thing to do to scale this protection of springs across kind of Africa in this context? So I want to ask, given that someone got diarrhea and they drank from a protected spring, would they have not got diarrhea had they not drunk from a protected spring? And that probability is very low, which is actually surprising because it tells us that actually it was something else. It was, children would likely have still had diarrhea even if the springs had been protected, given they drank from an unprotected spring. So it was something else than the protection of the water springs in this manner that has the effect on kind of reducing childhood diarrhea. It could be the educational program that went in and talked about that. And so this analysis can't tell us what that extra thing was, but it kind of suggests to the kind of NGO to kind of look for alternative explanations and perhaps run another control trial and scale that thing up if it has a bigger effect and so forth. So that's the kind of last thing. That's the paper there if you're kind of interested. And the last thing to say is I haven't really talked about Spotify at all here. So what has any of this got to do with Spotify? So I'll give you a kind of brief overview of some of these things. I'll just focus on the kind of last one here. So if any of you have listened to Spotify, you can go onto the homepage and songs are recommended, you listen to them and so forth. So a counterfactual question I might want to ask is, okay, given that somebody listened to a certain type of content, song, podcast, whatever, and they were engaged, they kept listening to that style of thing, I want to ask, in that context, had I shown different content, would they have still been engaged? This could suggest other things I could recommend to them or other things I shouldn't recommend to them because it wouldn't have a good impact. And so doing this actually is a counterfactual question and helps me learn something new about that user. Right? On top of all the data I have about them, I've now inferred that a certain type of content for them was linked with enjoyment. So I update my knowledge about any unobserved things that might be going on, their mood and various other kind of predispositions to certain genres and so forth. And in that context, I can now make more accurate inferences and so forth. So that's kind of my entire talk today. I talked about counterfactuals, why they might be useful. And I'd like to note that there are lots of more applications of Spotify beyond those kind of ones. So we're currently hiring, so if people are interested, please come and chat to me. Always interested to talk causal inference as well. So thanks very much for your time, and that's me today.
Thank you, Kieran. Okay, we'll take questions now.
Isn't that in itself a problem of counterfactuals, which you are in sometimes not solving in the model? As in, how can you be sure that these are all possible confounders or factors of risk? And if so, it seems to me that this may be some sort of an infinite regret of possible counterfactuals that we're not taking into account.
Yeah, it's a great question. So if I kind of repeat the question and so forth, it was that even if we're kind of reasoning in a counterfactual context because there can be hidden confounders going on, counterfactuals might help us update our knowledge about some of them, but perhaps not all of them, and this might still kind of lead to, bias in the true kind of type of inference we might want to perform. So that's definitely true. But now when you just want to compare counterfactual inference to, let's say, standard Bayesian inference or even inference just using do conditionals and so forth, because in the counterfactual context we're observing things about the world and then updating our knowledge based on that, we have more information to kind of about those hidden confounders to go on. We don't necessarily always have perfect knowledge. There's still things we're unaware about, or even if we update them, maybe we don't perfectly update them to a point distribution, maybe it's still a smaller range of the kind of distributional space and so forth. But without doing that update, we would have nothing. So in the kind of standard case, we would be an even worse case. So it's not saying that counterfactuals will always give you the right answer, but that counterfactuals compared to other forms of inference will get closer to the right answer because they tell you something about those hidden confounders.
Hi, I just want to ask about the diabetes example again. So you said that you'd have an issue there because the diabetes has such a high prior probability that you might still get a wrong output if you use standard Bayesian inference. I wanted to ask, do you think you could run a similar increase in the accuracy by using something like the more weighted to the likelihoods rather than using counterfactual? I don't know if you compared that at all.
Yeah, so it's an interesting question. So when we were kind of doing this, it was at a company called Babylon Health, and they had discovered this issue when they were doing the standard diagnosis, that in some cases you got these weird kind of cases where it was saying a disease was really likely, but there was no causal link, or a very weak one and so forth. So their approach to doing that was some form of reweighting in some sort of ad hoc manner. So they'd look at all the cases where they found it happen, and then just in those specific cases reweight the algorithm so it kind of made the correct or more accurate choice in that context. So what was cool is that the counterfactual didn't have to know about this, or it could discover this in a more automated way, so that you wouldn't have to be made aware that there was an issue to then go in and fix the model to make sure it didn't happen. And so, in principle, it's kind of very closely approximating this reweighting kind of procedure, because it's updating our knowledge and saying, okay, this thing is really likely, this thing is less likely, and now it's looking at the likelihood between those two things, given that this one has, it's reweighting them given their causal effect on top of the likelihood of them being there in the first place. So it's kind of doing reweighting in a more kind of, generalizable, foundational way, rather than kind of seeing it and then in an ad hoc fashion fixing those. But yeah, in effect, that's kind of what it's doing.
We have time for maybe 2 more questions. So on the examples of counterfactuals and Spotify, so you were mentioning the engagement and the current content. So when you say current content, is it the content you actually put light and put it to the library or just play it? And also do you measure engagement time, that how many seconds they engage, or is they actually just scrolling through?
So in this context, it would be given that they have listened to a song for at least a certain portion of the time. So let's just focus on music kind of for a second. Oh yeah, I'll repeat the question, sorry. So the kind of question was, in this case, what does it mean to kind of, engage with a certain piece of content? Do we listen to it? Are they just scrolling through a playlist and kind of so forth? And then the outcome, the engagement, how do we measure that? Is the length of time they listened to the, content for, or is it that they were, they listened to the content and then went straight to the artist's homepage because they loved the song so much they wanted to discover more music and so forth? So it really depends on the context in this case. So for us and how we applied this, what we did was we looked at whether a user listened to a specific track for a certain proportion of time, and then we inferred after that, did they then return to listen to either that same track or a track by that same artist in a kind of frequent way over the next week. That told us that they liked that content by that artist. And we want to say, okay, in that context, had instead of them listening to that track, they listened to a different track for at least the same amount of time, would they have had the same level of engagement with that track's artist? Would they have listened to it as much or more than the previous one? And if the answer to that is yes, then okay, this new track is a good thing to recommend to that user, right? They can now discover this new artist based on their taste and some other factors we kind of know about them. In the same context, had they listened, they would have listened as much. But if we figure out that actually, had we shown them a song and they wouldn't have engaged as much, then we shouldn't recommend that to them. It's not something that they would enjoy and so forth. So that's kind of how we formalized it. But there are many changes to that. You might kind of say, instead of level of engagement, you could talk about whether that user formed a good, sustained relationship over the following few weeks with that artist. That could be a different kind of level or type of engagement rather than just listening. It could, and so you could change all of that and see how it's going on. But I guess the point is that the counterfactual way of, formalizing this question gave us new information. We've updated our knowledge. They listened to the song and they liked it, whatever like means. That's telling us something about that user we didn't know before. And in that context, we can now ask, okay, if we change what they listened to, would they have liked it as much or less? And so the counterfactual context gives us more information than just kind of standard reasoning from some sort of observed correlations.
If I understand properly, at your definition of valuable counterfactuals, you started with a data set, then you built a class of Gaussian networks that validate this data set. And from this, you get your valuable counterfactuals. How do you deal with error of measurement? Your data being playing wrong, some of the data being playing wrong?
Yeah, absolutely. So the question was, given that we're learning these types of things from data, error could kind of creep in some sort of reasonable ways by how those variables were measured in the first place and so forth, and how does one kind of account for that? So in the model that we kind of showed, we had these noise terms kind of that were independent of each other in this context and causing the observed kind of things. And so any kind of error in how we've measured or collected this data should somehow be in that part of the kind of causal model. So in the learning process, we're both simultaneously learning the function, the mapping between the observed variables and so forth, but also trying to infer the distribution of these unobserved nodes. So if there's some sort of error, the hope is that it will be pushed in there. And so you can make some assumptions about how reasonable that is and so forth. Perhaps in a certain type of kind of data set, the error is such that these noise terms have to be correlated to be perfectly explained, and we're assuming that they're independent here and so forth, but you can weaken these things. But the idea is there can be noise and error about what's going on, but now in the counterfactual context, what's cool is that when we observe something, someone did a certain action and they saw a certain outcome, for that user, that tells us something about them as a kind of individual. It updates our knowledge about the specific distribution of the noise for them or how inaccurate our model is for them, and we can kind of account for that a little bit with this extra observation. So that's in a sense why counterfactuals are more kind of precise as decision-making tools than just talking about just standard kind of machine learning models.